All right, so a couple announcements. I'll just go ahead. It's 8. I would I would log on again. Well, let's do things in a couple orders. Find a partner, because we're going to make friends at this conference. 4 hours is a really long time just to listen to Colin and I, so it's probably somebody more pleasant to speak with. So get with your partner, and then I'm going to ask whose partner traveled the farthest to get here in about 5 minutes.
Hello, partner.
And your partner's on either side of you.
Yes, you can make multiple friends here. Okay. Oh, this is great. We got the best helper. You've been through this, most seasoned.
Yeah, the problem is that I don't know anything about ArviZ.
There's a version of this where everyone installs TensorFlow and PyTorch, which they don't play nice together. They sort of look for the other one and delete them. So it's, that would have been a really fun installation. What is PyTorch and Piano that don't like each other?
Yeah, there were a couple that just clobber each other. But we don't have to install them all for the tutorial. But yeah, try installing every deep learning framework in your CI.
So what is the installation procedure?
Yeah, so so they have their pick. They can use Conda, they can use pip, they can use Docker, or they can use Binder. So if worst comes to worst, just have them hit the Binder link and it'll fire up the container.
It's like Conda to install.
Yeah.
That one's not up on any screens.
This one's not up on any screen.
Okay.
This is my floating,
Okay, I didn't know
I'm gonna mess around laptop.
You're speaking as though I'll see that.
Oh, I am sorry. It's all on the video. So Conda, pip, Docker, Binder. I would probably if they don't know these two, they probably don't know this one. So. And then worst case, just hit the link.
Okay.
And we also just put the link right at the top.
Okay. All right.
All right, we got a couple more minutes. I would also get set up, so I would fire up a Jupyter notebook if you have it running. The install instructions are in the README of the repository. If your computer's locked down or anything like that, you can just click on this Binder link, and after a couple minutes, you'll have a VM on the cloud. The cloud is way cooler than having your own computer these days, so if you want to be with it, don't use your laptop.
We've got a couple of people who come around, I guess who come around, and if anyone just wants to raise their hand if you're having trouble getting this stuff running, there can be some trickiness.
Pat? I mean, this room I think is going to fill up, but there were a ton of people who showed up at breakfast at like 7:50 or something.
They'll come in late, huh?
Yeah, I think so.
All right.
I might just write the, I guess the Slack thing exists too, but I'll write the GitHub repo.
On the board? Oh, one thing, so we got advised. Apparently you can hear if you stand in like this range, and then if you wander around and use a whiteboard, we'll drop off on the audio. Cool. And then I'll have a mobile mic, so just be mindful. Don't say anything important while you're that far away.
Perfect. Canyon dash 289?
Just Canyon here. Canyon 289. And the Bayesian model evaluation.
If you get back to running an interactive session and mount your position on the doing crazy, but you already have that.
All right, so welcome. So, for the first one, who thinks their partner traveled the farthest to get here? It's a quick one. You seem very confident.
New Zealand.
Okay, that is going to be really hard to top. Wow, we really hit the maximum of that distribution really quickly. Okay, let's go. Who thinks they can beat New Zealand? Who thinks they're second? We'll go with the slightly N-1 for Max.
North Austin.
North Austin, yeah. We're
North of 51st, or?
yeah. Let's keep sampling here. Anyone closer? Slept outside the conference center?
I work 4 blocks away.
Okay, that's going to be a hard one to beat on the minimum of the distribution.
Anyone at UT?
Anybody live in this?
Yeah, did you sleep? So that's our informal sampling for the morning. We started the intro. So I'm Raveen. I'm co-presenting here with Colin. We'll be splitting up this tutorial, and I think if you'll get a sense when we go through this, I'm more of an applied guy. I work in industry. I guess Colin works in industry, but I've come from industry, kind of fell into Bayes, and then I use it in a very applied sense at a company called Sweetgreen, who Rebs also works at. We try and get healthy food to people. And Colin here, I'll let him give him his own intro.
So I'm a mathematician in former life, actually educated in Texas. Spent a lot of time in Austin. And I'm also one of the contributors to PyMC3. I'm really, I can help you out with applications. I'm really interested in how these algorithms are implemented. And so if you have any specific questions about implementations, or if you just want to talk about later in the week sometime and sort of geek out about how MCMC works, I'm really into the theory as well. So I think we can all answer all the questions you'll have about this tutorial, but if you want to really geek out about something, sort of the applied stuff, Raveen's great with, and the more theoretical stuff I would love to chat with you about.
Cool. So show of hands, who here has used a PPL or Bayes theorem anywhere? Stan, PyMC3, any of those? Third of the room? Who here has heard of Bayes theorem before they walk into this room? And then who here is just like the first foray into it? Like you're just starting out and you want to get into it. All right. So I think we have a relatively seasoned room. We were pretty lucky this year at SciPy. We had 3 Bayesian tutorials. You had Alan Downey's, which was in the morning yesterday, and then you had Eric's, which was in the afternoon, and now we have this one. To kind of set the segment of where they go and to encourage you to look at the other ones, Alan Downey's tutorial, if I say it, is pretty much like building the bicycle at Bayes. You start out with the nuts and bolts, and you build this simple algorithm. You don't use any, other than Numpy, you don't use any PPLs or anything like that. You really just, you build the bike, you ride around, you sample distribution, and you get off. That was this tutorial. Eric starts out with probability, and then he jumps into like the car of Bayesian inference, which is a probabilistic programming language, PyMC3. Now he doesn't show you anything about the engines and the internals. He just says, here it is, here's how you drive it, and we're good to go. In this tutorial, we're going to skip past. Actually, we're going to go really quickly through the basics of Bayes, and then we're going to jump straight into how to diagnose the engine of the PPL. So PPLs, when they work, they're great, but just like sometimes like a clunker, when they start sounding funny or whatnot, you got to dive in and you've got to kind of figure out what's going wrong and make adjustments and go. That's what we're going to be doing in this tutorial, is diving into how to diagnose, plug in your ODB reader and figure out where to make your engine work better. So we're going to be teaching through a combination of notebooks and slides. So I would fire up a Jupyter Notebook server. The notebooks are located in the notebook directory. We'll be going through 1 through 4 in the agenda. We'll leave 5 as a bonus for your own time. When you click into these, there'll be instructors, which is the one I'll be going through. You'll have your activities, and then there will be a solution. So I would advise you to try and do the activities first yourself, and then look at the solutions later. But you're adults, I'll let you learn at your own pace. So let's talk about Bayes theorem really at a high level really quickly, and then jump into our first activity. So for those who haven't seen Bayes theorem, this is the sort of canonical formulation of it. You have 4 pieces, 2 in the numerator, 1 in the denominator, and then the thing you're trying to estimate. And it comes out of the law of total probability. So breaking it down, you have a prior. So you have an estimate of what you think my tutorial abilities are like. You can't actually measure my tutorial giving abilities. It's my brain, and you can't really get in there with a probe. But you think there's some ability of me and Colin to give a tutorial. That's your prior. What you're really looking for then is, if you jump down to posterior distribution, after you've seen this tutorial and you've collected a bunch of data points, you'll have an estimate of how good Colin and I are giving tutorials. So you're going to get a bunch of Ys over the 4 hours watching him and I speak, and you'll get a better estimate of how good we are, our latent ability of giving tutorials. The tricky part, which a lot of people get confused with, is the likelihood. The likelihood says, given your estimate of how good I am at giving tutorials, this is how probable the data is. So if you think I really suck at giving tutorials and I do a good job, you can be like, well, I'm sort of surprised. But if it matches, then If you think I'm good at giving tutorials and I give a great tutorial, then you'll get another value. The likelihood is what turns your estimate and then the given data into some sort of probability value. And we'll have a whole tutorial on that, or sorry, a whole activity on that to build that intuition. And the last term, which is the one we're going to ignore the most in this tutorial, is this bottom, the marginal distribution of the data. In most modern Bayesian applications, you really try to avoid computing this. It's hard to do analytically, or impossible to do analytically by pen and paper for most applications, and it's super hard to do computationally for large problems. So in Alan's tutorial, he does grid searches, which are great for small problems, but as you expand to a larger base of problems with more distributions and whatnot, it becomes impossible to run a grid search before the sun explodes. So the trick is to get rid of this marginal data. There's two alternative formulations. I threw them in here because sometimes you see them and they can throw people for a loop, but there's a likelihood notation where they swap out the P for an L and they move these two terms around. And sometimes you see this. The reason defined as a proportion, the reason being is in most places we don't care about the Y. We just care about the product of the numerators here, the likelihood and the prior. Even so much so that if you've seen John Kruschke's book, it's an excellent book. I advise reading it. He defines it with puppies, and you've got this really lazy puppy that does nothing. So this was very intentionally chosen. You've got these puppies hard at work, and one that really just not useful to us at all. So what I want you guys to try to do is open up the model fitting notebook, and we're going to go through this together. So I'm going to go through it through the solutions because I trust my life coding ability, but I want you guys to type this in yourselves. I would say you guys are welcome to interrupt with questions at any time. Either Colin and I can answer, and we'll probably flip back and forth depending on who's got more expertise in the area. So we'll do the classic, what's called beta binomial problem, or the coin flip problem. What we want to do is we want to estimate the proportion of water on a planet. And so the setup here is you're welcome. You're at a university. You're back in grad school, and you want to figure out how much water is on a planet we don't have many observations about. We just found out there was a 10th planet, or sorry, I guess 9th planet now in our solar system. I was messing up with Pluto. What we have here is our first exercise. So in this model, we have two things, and I want to ask, what is the prior in this model? Does anyone want to shout it out? No? It's too early? The uniform distribution, and why is it the prior?
Because essentially it's the distribution we assume at the beginning.
Yes. That is exactly the answer. So it's a distribution we're assuming for this planet. A uniform distribution between 0 and 1 is saying that the planet could be 0% water or 100% water. We just don't know. So we're going to just say, without any data, they're all equally likely. And then in this model, what would the likelihood be? I'll take on someone else. Also, you can use elimination. There's only two things in this model. So
Proportion of water.
So yeah, it is. But what's the distribution that makes up the likelihood? It is the binomial distribution. The binomial distribution is a really good distribution saying if I have n Bernoulli events, how many what's the probability I could get those? So if I have a coin and I get 100% heads, what's the probability that'll happen if I have a fair coin? So 50-50 coin, what's the probability I'm going to get 100% heads if I flip a coin? So what I want you to do is if you can use any PPL in this tutorial. ArviZ works with them all, so if you know Stan, use Stan. If you know PyMC3, use PyMC3, MC, Pyro, whatever. What I want you to do is try and build a model that'll estimate the proportion of water. And I gave you some dummy data here. So if you can, code up the distribution, or sorry, code up the probabilistic model that'll estimate the proportion of water on this planet. And you can work with your partner to do so. I'll give you about a minute to try it.
This is sort of tossing you off in the deep end, and if you feel like you're in the deep end, just raise a hand.
We're here to help.
Come by and say hi.
Yep. All right, anyone want more time? Anyway, just a quick one.
Has someone gotten a model to fit? Is anyone panicking when I say
Code is already filled in, bindings, I got it.
Yeah. So yes, you're welcome to copy and paste. That is an acceptable solution. Please feel free to copy and paste it. This is the hardest activity to wake you up in the morning. They'll go downhill from here.
fitting a probabilistic model at before 8:30 is a whole thing.
Yeah. Enough so that I'm not going to do it. I'm just going to use my pre-canned solution. All right. Now that I've shaken you awake, this is the only time I will ask you to write a probabilistic model from scratch in this tutorial. After this, you can just copy and paste in the solutions, and that'll be fine. But let's run through it together. So, oh wow, that's a really bad error for this tutorial. All right, let me restart my notebook. Yeah, that makes sense. All right, let's try this again. All right, so we'll walk through this together real quick. So you have your imports. In this case, we're going to load in PyMC3. This is our PPL. Colin and I are a little biased because we contribute to PyMC3. But again, if you use any other PPL like PyStan or whatever, load up whatever you prefer. Then we're also going to load in Numpy just to generate some data, ArviZ, which we'll go into further about how to criticize models in Matplotlib. And what we're going to do here is we're going to take our model, or we have our data. So in this case, we've seen 3 observations of land and 2 observations of water. And we're going to say we have this many water observations and this many total observations. So for water observations, we're going to have 2. And then for total observations, we're going to have 5. And what we're going to do here is we're going to have our PPL, in this case PyMC3, fit the model for us. So what it's doing here is we've specified our prior. We don't know what the distribution of water is on this planet. It's somewhere between 0 and 1, but we'll take them as equally likely. And then we're going to say that we think that there's this, the likelihood will be this binomial model. That it follows this sort of coin flip model that it could be 0, it could be 1, and there's some probability, there's some proportion in the middle. So there could be 70% water, there could be 20% water, and then given our data, this will tell us the probability of that. It's much better visually. I'm going to use ArviZ, so what I would do is fill in the blanks. So we're going to use AV plot posterior. So after we fit in our model, we now have our first distribution that we can visually see through ArviZ. And we can get an estimate of how much water there's on this planet. With 5 observations, we think there's somewhere between 10% and 70% water, and we're 94% sure of that. We're gonna have a whole lecture just on this, so this one will just be going through all of the various bits and pieces. What I'm gonna ask you to do, and I can encourage you to copy and paste, is that if we get 100 more observations, if we get 400 more observations, 495 more observations, will we be more sure or less sure of the proportion of water on this planet? So with 5 data points, we might be a little bit unsure what's going on. But once we collect a lot more data, what will happen?
More sure.
We think we'll be more sure. So I'll give you, actually I'll just run this with you. I'm going to run this notebook. The PPL will fit again. What you're going to notice here is some magic's going to happen. Colin is going to talk about this magic in about 10 minutes. So we'll talk about how MCMC works. We go down, and we become very certain about the proportion of water on this planet. In fact, we're very, very sure it's between 0.4 and 0.4. It's so much so that the error is in the 3rd decimal places, not in the 2. So now we're very confident that this planet is about 40% water. Up here, it could be anywhere between 0.1 and 0.7 because we only had 5 total observations. Down here, we have 500 observations. And so here's our distribution. If we end up with a new planet and we just see 5 observations of land, when we run this.
So these observations only affecting our likelihood? We're not rerunning the trials? not having new priors?
So with Bayesian modeling, you set a prior once, and then your PPL will take all the data into account and give you a posterior. It does it all in one shot. So Colin will talk more about this in his section, but there's usually no iteration in the sense that you take one observation and then you run your model, and you take another observation, you run your model. Modern PPLs take all your observations in one shot, update your posterior.
So that's basically the likelihood.
The likelihood distribution will give you what's the probability of your parameters given the data you've seen. And I'll defer because we have 40 minutes on that. So you'll get your fill of how that works. With our new planet, since we've only seen land 5 times in a row, when we pull up our posterior distribution, you'll notice it does not look like a normal distribution. What it's saying is that, well, it's very likely that this planet is just a desert planet, but there's some tail that maybe there's some water, and it's very unlikely that it's 100%. It's not likely at all that there's 100% water. There's no chance that it's 100% water, and there's very little chance that it's 60% water. And so this is the magic of Bayesian inference. You start with having your priors. Usually, it could be anything, but a lot of times we'll say uniform. You have no idea what's going on. You see some things. When you see a little bit of data, you become fairly sure. And then when you see a lot of data, hopefully you become very sure about what's going on. What we're going to cover in this tutorial is how to diagnose this MCMC portion. So this magic that's happening in this red box, we're going to dive into that and how to see what's going on. And then we're also going to dive in how to use some of the plots in ArviZ to diagnose your models, like we have these two, a trace plot and an autocorrelation plot. And then how to use the other ArviZ plots to make some estimates of your parameters. So this is what's called a force plot. This is section 4. The first model, we're very unsure about the proportion of water, so that you've got a very wide posterior distribution. With a lot more observations, you become very sure. And then with our desert planet, it's more skewed to the left because we think there's almost no water on this planet. So that's to frame the tutorial. What I'll go through now is Notebook 3, the end-to-end workflow. So when we cover, a lot of times when we cover Bayesian statistics, maybe in the other two tutorials, you cover just a small portion, which is what the algorithm, the intuition behind the algorithm and some basic search strategies. But there's actually a whole bunch of things you can do with statistics. It's not just one piece. So we're going to frame this by talking about other versions of statistics. So Bayesian statistics versus frequential statistics. Bayesians ask, given the data, how likely are my parameters? And frequentists usually say, given these fixed parameters, what is the probability of the data? So Bayesian statistics tends to flip the model, or flip the thinking of how you go with, how you use data and models. One challenge I find with frequency statistics is that I usually have to follow a flowchart like this to find the particular model that fits your data. Bayesian statistics tends to be more flexible at the outset, so it usually ends up being less of a prescription and more of a challenge to figure out what's going on. But once you have it, you can mix and match pieces and build what you need to do what you need to do. Bayesian statistics versus machine learning. So we're going to cover linear regressions with Bayesian here. I want to point out linear regression, a linear model is a type of model, and then there's various ways to get the parameters for your linear model. So the way you learn in high school is the quadratic approximation, which is where you just get the minimum r squared, and that's how you get like the alpha and the beta for your coefficients for your linear model. You can also use deep learning to do this. You can use a neural net to fit a linear model. You can use a decision tree to fit a linear model, and you can use Bayes' theorem to fit a linear model. So the linear model is independent of what you use to do parameter estimation. Bayesian models just help you with parameter estimations. People conflate the two topics, and I want to split them apart. But the big point I want to make is that no matter where you are, even if you're in traditional machine learning with decision trees, there's a lot of things you have to do. It's more than just fitting a model. There's validating that your model didn't overfit. There's diagnostics. And there's loss functions. There's making predictions. So in linear regression, or let's say deep learning, you fit your parameters using the backpropagation algorithm and minimizing the loss. In Bayes, we fit our parameters using MCMC or ADVI, or there's actually a whole bunch of different ways to get your parameter fitting. You have your model parameters in deep learning are the size of your neural nets, right? The height and the layers and the activation type in your neural network. In Bayes, it's distributions of graphs and priors. So Bayesian statistics has analogs with all the other types of machine learning algorithms as well. If I talk about inference particularly, there's a bunch of different ways to do inference within the Bayesian space. There's what's called conjugate priors, grid search, which is what Alan Downey did. Typically, people these days use MCMC. That's what Stan implements, and that's what PyMC implements. And then some people use variational inference. MCMC, though, is like the go-to method. And then there's a whole bunch in here about nomenclature. I won't bore you with this at the moment because Colin is going to talk a lot about this section. But know that MCMC is a class of algorithms. It's not just one algorithm. He'll be going over 2 Metropolis Hastings and Hamiltonian Monte Carlo. And lastly, there's a lot of different probabilistic programming languages. So a lot of people took these algorithms and then made them their own. So just like neural nets have frameworks like TensorFlow, Caffe, and MXNet, there's a lot of different implementation of Bayesian probabilistic programming languages in many different languages. ArviZ aims to support them all. So you can use whatever works best for you in any language, and it'll work well in ArviZ. What we're going to specifically focus, though, in our tutorial is Python, MCMC, and then PyStan and PyMC3, which is our PPLs, our inference methods, and our language of choice, being at SciPy. And the last one here is the end-to-end Bayesian workflow. So I found this to be the best slide or the best single graphic of all the pieces of a Bayesian workflow. A lot of times the tutorials fit on or focus on this one piece. But in practice, you have to do all of these things. And what we're going to focus on actually isn't even any of these steps over here. It's just this one step right here. How to evaluate and criticize your models once you've made a fit. So with that, I will pass the torch over to Colin. And I'll let him talk a lot about MCMC.
Awesome. Thank you, Veen. I'm going to switch over to some slides here. So how's everyone doing? Are there any questions so far? Maybe we're running slightly ahead, and so maybe just if there's any hands for any questions or maybe statements that are true that you've learned so far, just to get some audience participation going.
Are the slides in GitHub too?
Yeah, these slides are in GitHub. I messed up putting the CSS in there, and so they're not linked yet, but I will fix the front page and add the link. This one I pushed to my own server, which I did not change the name of the server. It's at pymc3.colindcarroll.com, but they are all checked into the repo. Yeah.
On the last workbook that we were looking at,
Yep.
got this kind of Bayesian model flow, and one of the boxes has fake data
Yeah.
and recover parameters. What's that all about?
Yeah, that's a really good question. So this is called the prior predictive distribution. And so when you write down your model, if you don't put in any observations, you can go and just run this simulation forward. So this is just simulation, and this is not doing like MCMC or anything. And this is really useful in that you can look at your data and say, did I model this correctly? There's a very good paper this year where some statisticians took a model that had been published. It was for, I think, pollution density in Copenhagen. And they found that, the prior found that the density, it was like reasonably likely for the density to be that of a neutron star, which is like way more pollution than one should expect in Copenhagen. And so they went back, changed the prior to be something more realistic to deal with physical constraints that like probably it's less dense than concrete, say. And so this is part of their workflow was showing that if you use this prior predictive, if you look at how this compares to physical quantities that like how dense is air, then you can improve your models and use more realistic priors. Yeah.
For posterity's sake in the recording, the question was how to simulate fake data and prior predictive. So.
Yeah, thanks. And the other reason for doing the simulating fake data and looking at the prior predictive is sometimes you write down a model that's not identifiable. So no matter how much data you get, if you do the same inference method multiple times, you might get different fits. And so then that's a problem with your model rather than a problem with like your modeling choices. And so you want to make sure that your model has a chance of succeeding before you run it. So that, we can talk more after as well.
Thank you.
Cool. Any other general questions from sort of the part one? Yeah.
PBL a couple of times?
Oh yeah. So that's probabilistic programming language, and very broadly, this might be a way of using random variables as variables in a computer program, and so being able to use them. And so this showed up when Raveen was showing the PyMC3 model. You can sort of stick a normal distribution as the mean of another distribution, and you can add those together. And so you can use them just as normal variables. Cool. Great. So we're going to get into sort of why you might be interested in using a probabilistic programming language next. And we're going to be talking a little bit about how to implement a probabilistic programming language. So has anyone here implemented an MCMC sampler before? This is awesome. So we have just enough expertise, but it'll still be novel to a lot of people. So I think we're gonna really nail this. This animation, we'll look at this again later. This animation is a Metropolis Hastings sampler. So the shading in the background is a two-dimensional normal distribution, and the Markov chain part of MCMC means that we're using the previous point to pick a new point. So you can see how they're very correlated points. And then the Monte Carlo means that we're doing some sort of simulations. This is all based on some physical intuition. The right-hand side we'll also talk about. That's a fun thing. Okay, so why do we want to use a probabilistic programming language? Is that often we want to model this uncertainty in our parameters. And so our parameters are often latent, things that we can't observe no matter how much we see. Right here, I've just drawn a normal distribution and then labeled the axes provocatively so that you might think that they have to do with profits. So maybe we don't know how much we're going to make next month, but maybe we have some guesses, right? And we would write this down as a distribution. The upshot of this whole section is going to be data structures, shockingly. And so we should also think about how we might store a normal distribution as a data structure. And so how are we going to serialize this? How are we going to work with this? How are we going to actually put a normal distribution into our computer? Once you have a distribution, though, you can answer a lot of interesting questions. Like you can ask, how likely am I to make more than $90,000 in this next month, right? And you can sort of tell that might be an area under the curve. You know, we might draw a vertical line at 90,000 and then look at all the area over to the right, figure out what proportion is over there compared to over to the left, and that might be our likelihood of making more than 90,000. You also might wonder how long your runway is. So maybe there's some secret number. I work in startups, and so there is some secret number of how much money you have in the bank. There's some number of dollars that you're bringing in each month, some number of dollars that you're losing each month, and you might want to do some sort of simulations that add these up in the presence of uncertainty, and say, boy, we could have only 10 months, or we could have up to 16 months. And this could be one reason that having a distribution helps. As another example, so I grew up in Connecticut, and like everyone who grew up in Connecticut, there were golf courses nearby. So this is a golf course example. I don't play golf, though, but when people go out, there's often 4 people going and playing together, and if you do, par turns out to be really good. So if you can shoot par in a hole, you've done pretty well, but for the sake of this example, we're going to assume par is what par means in English, which is like average. And so we might have 4 players, and they have some chance of shooting below par or above par on each hole, right? So they might do really well and shoot 2 under par. They might do less well, but I think still very good, and shoot 2 over par on a given hole, right? And we might send 4 people out to play golf. This chart is something that we can't actually observe, by the way, right? We can have people go out and play tons and tons of golf, and we can get an empirical estimate of all this, but we wouldn't actually know this, right? And we might want to estimate this after a round or 2, after seeing what people shoot for 18 holes. But let's suppose that we have this. Once we have this, I'm sort of trying to convince you that distributions are a nice thing to have. Once we have this, I can go through, and I did go through, and just simulate 18 holes of golf 10,000 times. And then I can have a histogram of how these players do over 18 holes. If there are any golf lovers getting angry here because like not every hole is as easy, you can't really shoot 2 under par on a par 3, I don't know. But here's how they do after 18, and you might go back and look at their distribution. So player 1 either shoots really well or really poorly, and you can see that that gets reflected after 18 holes and just having a very wide spread of scores that they get. Player 4 has a very symmetric distribution, and that gets reflected in a very symmetric distribution later. You might also see that here I marked their average score. This is hard to do in your head, but easy to do with a computer, with that dotted line, right? So player 2 is overall the best in expectation, on average. Then player 4, then player 3, then player 1. And so on average, you'd expect on any given hole, player 2 to win the most, then player 4. And so when we go to playing 18 holes, really what's going to happen is every time they play this stroke play match, you'll just grab one element from this histogram, and you can sort them and say who won, who got second, who got third, who got fourth. And this is, I sort of want to convince you that if you're using sort of point estimates or traditional machine learning, this would be fairly hard to do. You might grab the mean score that each player would get, and then you'd have one number for each. It'd be hard to do this sort of analysis. There's another way people play golf. I think a lot of people go out and wager money on golf, and so they do what's called match play. And so you do the outcome of each hole. So whoever wins each hole, gets 1 point, and then after 18 holes, whoever has the highest score wins. So match plays we can also simulate here. I did tiebreakers as everyone wins. That's not actually how people do it, but here you can see player 1 ends up doing quite well despite having the worst average score. So remember, player 1 is the player that sometimes does really well and sometimes does really poorly. And that ends up in match play letting them often just win holes. So this is the sort of modeling I want you to think about when we're thinking about doing probabilistic programming, doing MCMC, is we're really thinking about all of our data as being probability distributions, and we're really thinking about sampling from them, and then we have this flexibility once we have our data in what sort of questions we're gonna ask and what sort of questions we're gonna answer. So that's our big motivation for probabilistic programming. If anyone's really interested in golf, you could go and actually put the rules into this, but you don't need to. Any questions after this first bit? Perfect. Yes.
You mentioned if someone's really interested, they can put the rules into it. For this and also the previous tutorial, there are often examples where the rules were put into it. How do you deal with that? And not just make something that's rubbish if you don't spend time putting the rules in?
Oh, yeah. So if I was using this to actually estimate people's relative skills in golf, I would need to go and put the rules in. And this comes up in that workflow that Raveen was talking about. Usually you'll look for that specific behavior. And so I would want to verify, for example, that on a tie, you roll over the points to the next hole, and I'd want to verify that you can spot that behavior in my model. And so I would keep working before even introducing data in. This is during these prior predictive checks, and so that's where it would fit in.
And that would be you working with the domain expert.
Yeah, and sorry, the question was how do you incorporate these rules, and how would you work through this without incorporating those rules? The answer being you shouldn't work through this without incorporating those rules, and then pointing out that you would need a domain expert to work with on this, and that's absolutely true, that you would bring in a domain expert, you'd bring in someone who knows how to play golf, and work with them and make sure that you're modeling it correctly. Yeah, thank you, very good. Great. Okay, so what are we doing here? I'm happy that we're at SciPy, and so we can put a little bit of math on the board. We'll put a fair amount of math on the board. So what we're really doing is calculating expectations. So we've got some sort of probability distribution. I'm gonna often use P as my probability distribution. And we're calculating an expectation with respect to some function f. So f is gonna be some function of the underlying data. So f might be how many shots each player took on a hole. F might be how much money you made in the next month. And we're multiplying that against the probability of seeing that value x. So you can think about it as an integral. You can think about it as these pictures of distributions. And the whole reason that we're going to use MCMC is that integrals are often hard to do. If you're trying to do them with pen and paper, there's sort of a probability 0 that you'll be able to solve an integral. It's very special when you get to sit down and write down a solution to an integral. But you can approximate them by taking samples, these xj's, and if the xj's are drawn from the right distribution, the one that p of x is a density function for, it turns out that you can approximate all these expectations. And so this is the strategy that we're going to do with MCMC. So MCMC is going to be a way of producing samples from a probability distribution of interest. The reasons we want samples is so that we can do calculations like this. So secretly, we're doing an integral, we're calculating an expectation, and we're doing that by getting samples, and we need to make sure our samples are coming from the right probability distribution. So I find that this is often a slide that we miss when we're introducing MCMC. I want to make sure, because sort of the rest of this, I'm going to assume that drawing samples from the right probability distribution is a good thing. And I want to make it clear that the reason it's a good thing is because we want to calculate these integrals, and it's because we want to figure out how well people play golf. Cool. So how can we produce samples? This being SciPy, has anyone been involved with like random number generation, like on the computer? Right? There's this whole in sort of any in any programming language, there's often a random library, and you can generate normally distributed random samples or gamma distributed random samples, and you have this whole library of random number generation. The way most of these named random numbers are generated is by doing math. And this is pretty hard, but it's worth it if you want normally distributed random numbers, because everyone wants normally distributed random numbers. They're really popular. They show up in a lot of places. And so you have to solve this integral to do this. And the integral is sort of hard to tell. The picture's nicer. The picture, you have a cumulative distribution function. You choose a uniform random number. You pick that on the y-axis, you walk over until you hit your cumulative distribution function, then you drop down, and that's your random number. That's equivalent to solving that wacky equation up there. If you picked any symbol in that equation and asked me to solve for it, the one I would least want to solve for is that x up in the integral sign, because I don't know how to do that. But that's the one that you have to solve for if you really want to generate random numbers very quickly. So you do this integral, you invert it, and then you draw these random numbers u that are over on the right-hand side, and you figure out what your corresponding x is. And so it's really nice when you can do this. You can do it super fast. You'd rather use this than MCMC any day, but this is an awful hard task to do. So just we'll be appreciative for the people who have done these integrals. Another way of generating samples, this is called rejection sampling. So this is just doing simulations. Here I'm approximating pi, and I'm doing that by drawing two uniform random numbers. I'm adding together what their distance from their origin is, and if it's less than 1, I'm accepting. If it's more than 1, I'm rejecting. And I know that I should accept about pi of them. Really pi over 4, right? The area of the square is 2 by 2, and the area of the circle inside is pi. And so the ratio of acceptances to rejections should be pi over 4. So if I draw 100, multiply the acceptance probability by 4, I get some sort of approximation of pi. This is with 1,000. This is with 10,000. This is pretty wasteful, right? I'm wasting 1 minus pi over 4% of my computing time because I'm rejecting all these samples. Once you get up to higher dimensions, if you're in 20 dimensions, you accept about 1 out of a billion samples that you draw when you're doing the simulation. I encourage you to try that with Numpy. It's very fast to do this experiment. So we're going to look for something better than rejection sampling. Once we get more than, like, say, 10 dimensions, you're going to need something smarter. And that answer is going to be MCMC. Before I go in here, let me just keep taking little checkpoints on any questions on. We're doing like probably 2 or 3 weeks of a graduate course on MCMC right now.
So it's very hard to solve for x in that integral. Is it very computationally intensive?
So the question was the integral earlier was very hard to solve for. It's just so it's hard to solve for because there's like integrals don't often have closed form solutions, and there's a limited bag of tricks we have for doing integrals. And so I'm talking about solving them analytically. What we're doing with MCMC will be computationally solving them, and it's extremely computationally intensive. Yeah, sort of a repeated piece of advice is if there's anything you can do that's not MCMC, you should do that, because this is one of the more expensive things you can do with your computer. Cool, any other questions from this? So we're about to implement our own MCMC sampler. So the whole idea, I mentioned earlier that we want to calculate expectations. And so on the right-hand side, I've got in red, I've got the mean and the standard deviation, one standard deviation of my true distribution marked. And then in black, I've got this empirical estimate we get from the samples that we've already taken. So that empirical estimate is updating as we go. And our whole goal in doing MCMC is to try to make that empirical estimate converge faster. So get closer and closer to the true norm, or the true mean and the true standard deviation. And so there's a lot of work. This is what sort of current research in MCMC is making that circle converge more quickly. This one, you should think, hey, it's converging pretty quickly, but not that quickly. So this should make you both nervous about MCMC. It should make you realize that it's not magic. If we stopped after taking a certain finite number of samples, we might not have a very good estimate of what the true underlying distribution is. But it's also nice, there are theoretical guarantees that we have. If we ran this forever, it would get closer and closer. There's sort of asymptotic guarantees, and that's why we like MCMC. Here's another way of looking at it. So this is another animation, and what's happening is this is the same sampler, and it's drawing from a one-dimensional distribution now. This one-dimensional distribution is a bimodal, so it's got two modes, and they're both sort of normally distributed. And what you see on the top is sort of a timeline of the samples that we've taken in the past. One thing to notice about this is the samples that we're taking are very correlated, right? It doesn't look very random. It's very likely that the next sample is very close to our previous sample. This is going to be the problem with MCMC, is that our samples are going to be correlated, and we need to watch out for that correlation, because that a lot of statistics assumes that you have independent samples, and we will not have independent samples. Okay, well, so here's a full implementation of Metropolis Hastings. So to walk through this line by line, we initialize a position somewhere. Right, we're taking two arguments, number of samples and some sort of probability density function. So the number of samples will be how many we want to get out, and the probability density function will be something like e to the minus x squared is like a normal probability density. And we're going to initialize some position. Here I'm just initializing at 0. And then we go through in our loop, and we have a proposal distribution. The proposal distribution is a normal centered at our previous point. This is where the correlation comes in. And the intuition here is that if our current point is from our distribution, maybe a nearby point also has high probability. And so we're going to use our previous point and our knowledge that there's some probability density there to pick a new point. There's an accept probability. This is where the theoretical guarantees come in. So the accept probability says, what's the density at my new point divided by the density at my old point? If I have higher density at my new point, that probability is going to be greater than 1, and I'm always going to accept my new proposal. If it's got lower density, I might reject my proposal. Right? So I'm always going to go towards regions of higher density if it's proposed, and I'm sometimes going to go towards regions of lower density if that's proposed. And this turns out to do the mathematical bookkeeping just right, and you're going to end up sampling exactly correctly.
Is this just basically a random walk?
This is a random walk, and that acceptance probability is giving you the nudges that you need so that instead of sampling from the proposal distribution, that random normal, I'm actually sampling from this PDF up top that could be anything. There are a couple more technical details that you'd want if you want to do this. And the question was, is this a random walk? I'm going to get better at that. Any other? Yeah?
The output of the PDF function, is it a single number or is it a whole distribution?
Yeah, good. So the question is the output of the PDF function a single number or distribution? The output of the PDF function will just be whatever the height of that curve is at that given point. So if I pass in 100,000, it would give me the highest number it could possibly give. And if I pass in 120, it would give some sort of lower number. Good question. Da-da. Cool. Okay, so now we get to our interactive part. I'm stealing this from a nice presentation I saw about birds recently. And so we're going to be doing a quiz on trace plots. So this is a trace plot. I took 10,000 samples using that MCMC sampler from the previous slide. And on the left-hand side is a histogram of the points that I drew. And on the right-hand side is that little timeline of the points that I drew. And I'm going to teach you how to read a trace plot. This is called a trace plot. It's often the first thing people look at when they're diagnosing how their MCMC went. So there's a couple things that can go wrong when you're doing MCMC. If we take a very small step in our proposal, so if that proposal is np.random.normal, and if my scale there, so I pass in a location, if I can also pass in a scale or standard deviation. So if my scale is very, very small, I'll usually accept because it'll usually have about the same probability density as my previous point. But it'll take me a long time to get from one place to another. If my step is really long, I'm going to forget all about the local information that I have, and I'll often reject because I'll just jump way out into the void and there'll be no probability density there at all. So too big of a step will mean that that I reject the point, and that means I resample the point that I'm currently at. And so my chain will get stuck in certain places. And so for fast convergence of your estimations, you really want some balance of the two of those. Both very small steps, very big steps have these theoretical guarantees. So eventually you'll be drawing from the right probability distribution. But if you want fast convergence of your estimates, you want to get something in between. And so if we're looking at this, we're going to go through and I'm going to show you what the distribution is, and you're going to have to say out loud, and you don't have to say it loud, but you do have to say it. And don't worry about being wrong, because you're going to be wrong quite a bit, but you'll get right eventually. There's going to be about, 40 of these. So this one's, we'll go through just the easy ones. Your 4 choices are going to be small, big, good, or independent. So I'm drawing all these with either too small of a step size, too big of a step size, a good step size, or I'm drawing them from a actual independent distribution, and it's not being drawn with MCMC. So those are sort of like the gold standard. So this one's going to be too small. So when we do this, can we all say small? Small. Great. This one is going to be good. So can we all say good? Good. Right, and just the difference between small and good. This one's too big. You can see it getting stuck. So can you say big? Big. Great. And then this one is drawn independently. It looks kind of similar to good, and so this is where I get it wrong a lot, but can we say independent on this? Okay. So now we're going to start going through it. There's going to be 3 different probability distributions that we're going to see along this. I'm just going to pause for about 3 seconds, give your answer, and then I'll go and it'll show the true answer. Okay, so ready? Nice. 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 Okay, now we're at student T. Yeah. This gets harder. Yeah, independent and good is very hard. So that's independent. Here's another student. Nice. That was small. Nice. Nice. Sounds good. Oh. Here's some. Nice.
Good.
Nice. Nice.
Small.
Awesome. Thank you guys so much for playing that. I learned barn owls versus barn swallows versus song swallows, which was also a very fun exercise. So I think now we have some sort of intuition for sort of how you're tuning these steps, right? Small were pretty easy to spot, big were pretty easy to spot. The good versus the independent were sometimes difficult. Yeah.
Once you converge and if the step size is right, how close are you to approximating independent sampling for distribution?
Yeah, so you do, the question is once you converge and if the step size is right, how close are you to independent sampling? And so in some sense, asymptotically, you will be drawing from the correct distribution. And so if you shuffle them and like, depending on what you mean by close, you can't really tell the difference asymptotically. But for like mixture models, you can, and you actually need infinitely many samples. And so, yeah, it can be a complicated answer. But intuitively, you'll be very close. So here's what a real library does. The PyMC and Stan both do their best not to let you do a bad job. And so I cut off all the options that I had to put in here. I had to tell it not to do any tuning, to pick the right step size. I had to tell it to use a very small step to do a bad job with Metropolis. I had to tell it to use Metropolis because Metropolis Hastings is not a great sampler to use. But once you do all that, these libraries will still do multiple experiments all at the same time. So they'll detect how many cores your computer has, or you can specify, and it'll run this experiment multiple times. So we call each of these experiments a chain. This one's running 4 different chains, and we're seeing that same trace plot. So all these trace plots have been generated with ArviZ. The first ones I was just passing in Numpy arrays. This one I'm passing in a PyMC3 trace. And what's wrong with the sampler here? Too small. This is an easy one to spot. So you can see that not just because you're doing MCMC doesn't mean you're sampling from the right distribution. This is the impetus for using ArviZ and for doing all these diagnostics. And the other thing I want to point out here is if we start counting up dimensions, so I told you we're going to make a sharp turn into data structures. If we start counting up dimensions, suppose we're thinking about that golf example. You got 4 players, so that's one dimension. You have 18 holes, that's a second dimension. You might want to run 4 chains, so that's a third dimension that you've got there. And so you've sort of got a 3-dimensional object that you want to get out of here that's going to be 4 by 18 by, I don't know, by another 4 for your chains, and then you want to draw 10,000 samples. And so that's going to be a 4th dimension that you need. So you need this like pretty high dimensional thing. And so how are we going to store this? We're going to end up storing this with a wonderful library called ArviZ, or I'm sorry, Xarray. Sorry, I'm in my wrong. So I'm going to start down here. So this has some nice introduction on Xarray, but I think some of the developers of Xarray are here this week, and I encourage you to go thank them for this wonderful library. Xarray is built on top of a serialization library that is cross-platform. It's written in C. It's called netcdf, and Xarray is an in-memory representation of these netcdf files. And so an intuitive way, the way I think my working definition of Xarray is that it's pandas for high-dimensional data. So you get labels, you get high-performance computing on these, so you can do slicing, and then you get this added benefit of a serialization library that's really flexible and lets you like read and write very quickly. And so what ArviZ does is, and sort of the good idea ArviZ has was to take all these different probabilistic programming libraries, including just raw NumPy, so anything you roll yourself, and tuck it into an Xarray object. And so this will come with all these labels. And so we would have like player name, we would have hole, for which golf hole that they're on or something. And you can go through and slice by all these different options. Yeah.
Sorry to go back, but what should we do if the trace plot is not great?
Yeah.
Is that going to be a topic?
Yes. Yes, but the answer is usually the probabilistic programming library will let you adjust those parameters And most modern ones, you never have to even worry about that, but it's useful to know that's a thing that can go wrong, especially if you're implementing your own, but most of them will tune the step size automatically. You know, if you can read it with your eyes, you can often read it with a computer and just have the computer do it. So here's what X-ray looks like. Right, we've got draws and chains, so these are the two things that we're always going to have for our MCMC. Right, we'll take like 1,000 or 10,000 draws, and then we're going to have each chain will be an independent experiment that we do. And it'll have the data variables will also be labeled. So this one has mu and standard deviation. So going through, so here's some stand code. Who's used stand before? Yeah, awesome. It's a wonderful library. If you're using R especially, it's very fast. It's very good. PyMC tries to copy what stand does because they often do the right thing and do it very well. But this is what stand code looks like. So stand is its own programming language, and PyStan lets you write stand code and then compile it from Python and do your inference that way. So it looks pretty nice. We can go run our stand code, and then we can just turn that into inference data using ArviZ. So ArviZ will take all these objects from Stan, and it will eat those, and it'll give you back a collection of X-ray data, and then you can read and write that from disk just natively, and this is a wonderful place to be in. Just as historical context in the past, each of these libraries had their own serialization or not serialization layer. I think PyMC3's object that you use to handle traces has like 112 methods on it, and so that was quite a bit. And it's nice now to have a standard object to just do your calculations with. So I think I'm going to kick over to the practice. You guys have sort of listened long enough. So if you go into the notebooks and go to section 2.2, there are some exercises to do, and we're going to sort of take, I think 20 minutes was cleared for this. We're going to take 20 minutes and start using ArviZ and X-ray to do these. And so check out in the instructor section and check out in the notebook and start trying to work through this. Also feel free to get up and like move around a little bit. I can write down sort of when we'll go back to like talking, but spend some time trying to work on this, work with your neighbor, and get through this exercise.
Let's do an extra. Wow, that's a really annoying alarm. Well, so let's go through and remotivate what we're doing. I know we went through a bunch of MCMC, so let's go back to the second tutorial, and let's just open up the solutions, and I'll talk you through all the steps again. And so I'll make this more interactive. What are we trying to do here? What's the question in a one-liner? Someone want to shout it out? It's even on the board.
The research question?
Yes, what's the research question?
To estimate the amount of water on that.
Yes, so we started out with a research question. It has nothing to do with Bayes. It has nothing to do with PPLs or MCMC or anything Colin and I talked about. It's just a sort of practical question you'll get in research, which is, I need to figure out what the proportion of water is on, let's say, Mars or Pluto or whatever planet I want to have. You could have a different research question, which is, what's the occurrence of cancer when you've been exposed to cigarettes? In supply chain, I have a question of, what's the distribution of arrivals I get from a supplier? So when you buy a package from Amazon, it could arrive in 1 day, it could arrive in 5 days. You usually want it to arrive in 2 days, but in reality, it could arrive anywhere between 0 and 100 days or 1 million days. We want to ask the question, what describes what I'm seeing the best? And in this case, we want to say, what describes the proportion of water on a planet? In Bayesian methods, we can describe this in 2 ways. We can say, without knowing anything, I have this assumption it's between 0 and 1. There's a 0% chance there's water. There's a 100% proportion of water on this planet. In this particular problem, 120% doesn't make sense. 200% of proportion of water doesn't make sense. So we're saying here we want to go between 0 and 100. And then I'm saying, given a parameter value, how well does it describe my data? So given that I have 2 observations of water, Does it make sense that there's a parameter of 0% water on the planet? Not at all. Now that I've seen at least one observation of water, it doesn't make any sense that there's no water. But 20% still might be a reasonable value, 40% proportion might be a reasonable value, and 70% still might be a reasonable value, given that I have 5 observations. So they had a question about PPLs, which I want to repeat here. What PPLs do for us, which is what you won't see in, like, let's say Alan's tutorial, is PPLs make it easy for researchers to ask these questions, or even practitioners like me. I don't want to sit there and work with a bunch of NumPy arrays and write down all the steps that Colin did. Like, that's not what I'm going to do day to day. It would take me forever to ask a question. What probabilistic programming languages let us do is say, you know what, I think that water could be anywhere between 0 and 100 with even probability if I haven't seen anything. And I think that the binomial distribution is a good way of explaining what's going on with my water observations. It describes well, if I have 10 observations and so many water observations, what proportion is possible, what the, how well a parameter value explains a proportion. And what we'll end up getting is we end up getting this trace plot, or sorry, this posterior plot, which says with 5 observations, so 1, 2, 3, 4, 5, I'm somewhat sure the proportion of water on this planet is between 0, 0.1, and 0.7. That's the motivation behind Bayes, is to quantify the uncertainty in a mathematically rigorous way. So I don't want to just say, like, I kind of feel okay about the amount of water on this planet. I want to be mathematically rigorous and say, given probability, like strong probability fundamentals, there's a 94% chance that there's somewhere between 10% and 70% proportion of water on this planet. Doing this, though, I run into the problem that Colin just brought up and what you guys are working on right now. When you're doing research in a notebook, it's pretty easy to get these plots going, but when you have to then keep all the data together, it's really challenging. So this is a very bad notebook for reproducibility. And if we do science this way, I would not trust any cancer research, because if it's just a bunch of notebooks that people are carrying around with a bunch of MCMC algorithms doing a bunch of magic, you can't be really sure what's going on. In this notebook, I have just a bunch of cells and a bunch of MCMC traces, and there's really not a good way to now share this notebook with somebody else in a reproducible way. So the first motivation that we have for reproducibility is that given we have this complicated algorithms that Colin shows you that did all this magic of walking around all over the place. Let me keep going back all the way to the beginning. Given that I have all this magic that's estimating my distribution by walking in this MC algorithm, going here and there and here and there, I want to be able to store these values in a way that's easy to share with people. And the way that we did that with ArviZ is to put them into our Xarray object. So now we're going to dive into the Planet tutorial and making it reproducible. So we're going to start with the same Planet tutorial. I have 5 observations. 2 of them are water observations, 3 of them are land observations. I'll create my probabilistic programming model. This is the PPL portion, and I'm going to say that, again, without my prior is I don't know. I have a likelihood that says I feel like the number of observations follows a binomial distribution, and I'm going to generate a trace. In this trace, the one I have here in particular, there are 22,000 samples across 2 chains. Or sorry, there are 11,000 samples across 2 chains, and I want to capture this information in a way that's transferable and portable, because if I just show you this, you could dismiss my science and say that I did things poorly. I want to capture them in a way that I can hand them to you and you can continue the research. In PyMC3, the way we do that is we say ArviZ from PyMC3, I want to get this water data object, and actually I might need to run my notebook, so let's do that. So let's see if this works. Nope. So let's go through and do my imports. I'm going to use the white style. I'll input my data, which is fixed, and I'm going to let my PPL do its magic. So everything Colin talked about, which was mathematical and scary, Stan and PyMC do for you just in this one step right here. They do all the MCMC, they do all the random walk, and they figure out what your posterior distribution by all that math magic. It's all hidden in this one line. Over here, you'll see the steps. So we had 2 chains, and these chains took 5,000 steps each. And I have chains too. All this data though is right now in Python memory. If I shut my laptop down, it's all gone, and it's non-shareable. So what we want to do is we want to take our object, and we want to turn it into this inference data object. So instead of just having a trace floating around, we're going to put it into an ArviZ az.inference data object. And now we end up with our inference data object. We're going to observe our inference data object, and we have three things in here. We have our posterior distribution, because we generated a posterior distribution here, which describes our belief in the parameters after we've seen the data. And we end up with two other things here. We're going to, one of them is just the observed data, what we ended up putting into the model for what we've seen. And then sample stats are additional statistics around the sampling itself. We won't go into these in particular, but MCMC runs generate tons of data explaining how well they worked and how well they did. What we can do in particular is look at our posterior chains specifically. So we can take our water data, and then by putting in .posterior, we end up seeing the X-ray object that is our posterior distribution through the MCMC walk. And I know again there's a lot of concepts here. We have the model, we have our MCMC inference algorithm, and then we have our posterior estimation. What this here is our two chains for our MCMC walk, and then all the draws for both of the chains. So what X-ray lets us do is, like Colin said, it lets us store our inference run in a nice tidy package, where previously it's been a little bit challenging because some people in Stan would use one PPL, and it would have its own objects, and then PyMC3 would have its own objects, and then any of the other PPLs that you saw in the first lecture would have its own different way of storing things. And it was really hard to collaborate and go together. By putting it in X-ray, these things are standardized and easier to transport. You can also just save your objects to disk, so instead of just having it in a notebook and having to rerun your PPL model, you can put them in a way that you can just email to someone. So another horror of this is that by design, the models here run pretty quickly. Some models, though, take a really, really long time. So there's one that I ran in particular that took 2 days to run. I don't want to rerun that inference run every single time to figure out what's going on. The way to think about the random walk is that if I'm trying to explore this small space, it'll probably take me, 20 minutes to walk around and look at every desk and sort of feel comfortable with space. But if I have to do a really big problem, if I had to explore all of Austin, I wouldn't want to not write down where I'm going. I wouldn't want to keep it just in my head. I would definitely want to keep track of where I'm at, because exploring Austin would take a day, maybe weeks, or a couple weeks in particular. And if I have problems that are very large on the scope of, let's say, an entire country, I don't want to have to explore the entire country through a random walk every time. I'm going to definitely record what I've seen and what's going on, so I can then share it with somebody else so they don't have to retake that random walk. Unfortunately, with MCMC algorithms, sometimes you'll see some papers where they run the algorithm, but they don't provide you the results. So to reproduce that paper, you'd have to rerun everything yourself. And I've sort of screwed myself over in industry. I run a model and I come up with some estimations, and it took about 2 or 3 hours. And then I shut my notebook down without forgetting to save. And I would have to start the notebook again and then rerun the 2 hours worth of inference runs again. And that's no fun. So saving it to X-ray lets us save it to disk pretty readily. What we can do is in exercise 2 is we can then load that from disk. So the radon model is a particular model. In the 1980s in Minnesota, people wanted to find out, or the government wanted to find out, whether if you had a basement, whether radon was more likely to enter your home. This is really important because radon is radioactive and can cause cancer, and we want to help people avoid cancer. So what the Minnesota government did is they went to everyone's houses, they checked whether they had a basement or not, they checked which county they were in or not, and then they estimated the presence of radon in the home, given a lot of covariates, one of them being whether you had a basement or not. The reason the basement matters is one of the mechanisms for radon to get in your house is from the ground, and your basement is in the ground, the radon seeps in, and suddenly there's a lot of radon in your house, which is something you don't particularly want. The research question here is, does the presence of a basement, what effect does the presence of a basement have on the radon levels within a house, and particularly, what's the distribution? Not just whether it's 10 times more likely or 5 times more likely. how likely is how likely is 1 time, how likely is 2 times radon exposure, how likely is 10 times radon exposure, and how likely is 20 times radon exposure from the presence of a basement. Luckily, someone did all this MCMC magic for you. They wrote the model and they saved everything to disk. So you can just load it by saying ArviZ.load radon. Load ArviZ data set equals radon, and the radon object will automatically come down to you through the magic of the internet. Oops. So the radon data in particular, we've stored in the cloud on Figshare. When you run this, it'll download to your local computer, and you actually end up with a bunch of different inference groups. You end up with the posterior run, so all that MCMC magic has been run once on somebody's computer, and it's been saved. And you end up with also priors, which is running an MCMC run without conditioning on data, just doing it with what would happen with just your priors. We won't focus on priors too much, but the point I want to make is that you can save your model results to disk pretty easily, and this is what we're going to be doing the rest of the tutorials. We won't be running the MCMC algorithm in the classroom, at least of the activities. We've already run the NC models for you, and you'll just be loading the MCMC walks on your computer and just evaluating them. That's the research part of it. This is what lets you easily evaluate and criticize your friends' models. You let them run the MCMC walk and do the step size adaptation, all that, and then you just have to load the data and then just tell them if they did good, bad, or independent, just like we did in the earlier tutorial. I saw a couple questions.
Can these model objects ingest like fresh data and make predictions?
So this is one of the downsides in the Bayesian space. So the question was, can you then restart an MCMC run, get new data, and sort of do like online learning, as we call it for some of the other machine learning spaces? The answer is generally no. The unfortunate part, at least with Bayesian models, the Bayesian space right now in Python, is you would just have to take the new data and then retrain the model from scratch. That's probably the easiest way to do things. It is very challenging to update the model with new observations and with probabilistic programming languages.
Can you just score data though?
So you can score. When you mean score, let's be specific.
So I'm not talking about automatically reparameterizing the model based on new data. I'm just talking about making predictions based on the saved model object.
So can we do that with PyMC3? Can you generate a posterior predictive with an X-ray object?
You'd have to write your own code.
Yeah, I think so. The unfortunate part is you could hack it. Since you have the X-ray object and the posterior trace, you could then write your own code to take those posterior, the estimates of the posterior distribution and generate new samples. I would say, while it is possible in practice and theory, the easier thing to do is just fire up your PPL, and a lot of them have built-in methods to estimate posterior predictive distributions. It's a little bit of an advanced aside.
Can we use so it seems like a lot of the advantages here are working in teams, right? What if you have multiple team members that have different data? Like one person runs their PPL, they sample, and they generate a new posterior. Can you feed that posterior in as a prior and then add your own observations to the same model? Is there a pathway for that?
Yes, there is. So you can definitely do that exact thing. You can load up your posterior distribution here, and you can get some estimates of what that posterior distribution may be and use that as a prior for the next iteration of the model that you would like. So the question here is like, let's take our planet model. If you're the first person doing research on a planet, nobody knows anything about this planet, so you're just going to say, I don't know what the proportion of water is. But now we've gone through, a researcher has taken 5 samples, they got some water, they got some land, and they're not starting from a naive sense anymore. They have an estimate of what the proportion of water is on this planet. Now let's say you're the next grad student in this office. You don't want to redo all the research that was done before you. What you can do is, like, let's say load up this inference data object, use this to figure out what the posterior was from that estimate of 5 samples, and then continue your research on with what's called an informative prior from previous research.
Where is the appropriate place to do that? Like, would you do this from? Does ArviZ make a IMC trace object, or then? So you're shaking your head.
Yeah.
Just to understand the relationship between ArviZ and.
Yeah. So ArviZ is trying to be language agnostic, and so most languages do not. ArviZ integrates with languages. Most languages do not integrate in the other direction. There are some that might in the future, but yeah, you would have to have your own way of re-extracting. But it's nice because it's already in there as a NumPy array, and so you would write your own wrapper to bring the data back into the PyMC.
So just to repeat the question, ArviZ right now integrates on top of other PPL languages. There's a one-way path to go from Stan or MC or PyTorch or PyMC3 into ArviZ. That stores the values for you in a way that's loadable from disk, but there's not an easy path right now to go back into a PPL for both of those questions. For the other steps in here, so ArviZ captures all this data for us on disk. The nice thing now is if I shut down my laptop, I'll still have my inference run, or I can email this inference run to you or put it on Dropbox or something like that, which is something that was really challenging to do with PPLs in Python in the past. The next thing it lets you do is it has, this is more of an Xarray thing than an ArviZ thing, but Xarray, by the way, is a fantastic package on its own right. You don't have to use it just with PPLs. But Xarray lets you store, essentially, if I really simplify it, instead of just a 2D Pandas data frame, it lets you store an ND data frame or Xarray object. And so in this case, we can then slice the data and ask all sorts of questions of it. So we can say how many different counties do we want to include in here. So if we take like this Atkin County had 5 observations. There were a lot of observations from the Anoka County. There's a bunch of other counties. We can use some Pandas tricks and Xarray tricks and see that there were 85 different counties included in this study. So if you were the radon researcher in the University of Minnesota and you want to reproduce this research or you want to continue on, you can double check real quick and see that this particular model covered 85 of the counties at the time in Minnesota. And maybe if there's more, there's less now, you can start continuing sampling from some of those counties or all those counties. How many variables are in this Bayesian model? So to illustrate what variables are, if we go back to our previous distribution, there's actually one variable here in the planet model. It's just the proportion of water on a planet. But as we start getting to more and more complicated models, like when we go to linear regressions later, there will be two variables in a model. We're trying to estimate, actually 3. We're trying to estimate the intercept, the slope, and a noise parameter. And models can just get increasingly complex from there. Some of the PyMC developers have models that have thousands of parameters to try and figure out the effects from all sorts of places. In this particular one, we have 3 variables, so they're all listed right over here: gamma, epsilon, sigma A, mu A, and sigma Y. So this is a relatively complicated model. We will not be covering a model that's complicated in this class or in this tutorial, but the point here is that the Xarray object lets us list out and see all the various variables that may be in an extremely complicated model. And then sort of as a trick here too, you can subset and take pieces of the chain as well. So a lot of times in an MCMC walk, the initial exploration will be really boring. So if I do a random walk, I might spend a lot of time here, and you might not want that portion. You might want the portion where I suddenly randomly start appearing in other places. Or if I was to explore Austin, you might not want the random walk where I'm just exploring this building. You might just want the portion where I've suddenly made it outside and I'm exploring the outside space. Xarray makes it fairly easy to go in and just take pieces of your random walk. And so with ArviZ and with PPLs, you'll rarely get to this point, but we just did want to illustrate that that Xarray is very full-featured, and you can sort of slice and dice your MCMC walks as you may please. All right, so I'll pause for questions.
Are there any features that it supports for, it looks like a lot of this is for PyMC3. Are there a lot of features that it supports for PyMC3 that it would not support for like PyStan?
So the question was, are there features for ArviZ supports for PyMC3 that does not support for PyStan? And I think in this case, I'm going to say PyMC3 and PyStan and Stan have feature parity in ArviZ. We luckily, on the ArviZ project, have PyMC3 core contributors, myself and Colin, and Osvaldo. And then we also have Stan contributors. So Ari, who's in Finland, he's a core contributor to Stan, and PyStan, and he's also part of ArviZ. So those 2 languages are very well featured. We recently picked up a Google Summer of Code student who was very familiar in MC, and he built out the integration for that portion. For the ArviZ project in general, we're happy to take contributors who use any PPL and help us build integrations. But the idea is that you can use ArviZ with any PPL, It's not just meant for PyMC3, and it's not just meant for STAMP. All right. Any other questions? So I think I'll go through the whole workflow again because we covered a whole bunch of steps. So the thing we want to do is we just want to know what parameters describe the world. You can't really see the parameters. You have to collect data, and you have to make estimates. So what Bayesian stats lets us do, what we can do is, given some data, we have a better idea of what the fundamental truth is, let's say, of the world. So we want to know something about the world, and the way we get there is we just take a lot of observations, and we sort of take that path. Now, the challenge, though, is the first challenge is, one, the math is really hard or impossible. So this is where we start using MCMC. MCMC is this magic algorithm, and in a certain way, it lets us avoid the math and just lets the computer do the random hard part for us. And what that ends up giving us is what we want. It's called the posterior distribution. And this is a better description of what the parameters of the world look like. So we don't know anything about the world, but we want to get to a point where we know a bunch about the world. So let's take some samples of the world. We'll take a couple of data points. Now we need a way to use that data we've turned and turn it back into math and in a concrete way of explaining the world. So that's what posterior distributions do. And what ArviZ does is lets us do this in a reproducible way. A reproducible way and in a way we can criticize. So the X-ray bit here is how we can do this in a reproducible way. What X-ray is saying is after we've done all this work of asking a research question, collecting data, and then running this computationally expensive MCMC algorithm, how can we store it in a way that we can reuse our work and without having to run the MCMC walk again? And how can we give our results to somebody else so they can use it in a reproducible way? What ArviZ is going to let us do in the next section 3, is how can we use ArviZ to criticize the MCMC walk? So while Colin showed you a whole bunch of math on the MCMC, I will wager to bet that MCMC still might be challenging for a couple of us. The idea is we don't want everyone in the world to have to know MCMC. Specifically, just like a car, right? You don't want everyone to be like an F1 auto mechanic to drive a car. You just want them to be able to drive the car easily and get from Austin to Los Angeles to Boston or wherever we want to go. And we want to have at least enough expertise to say if this car's on fire, it's probably not a good car to be in anymore. That's what ArviZ lets us do. It lets us just, it makes it easy to pass off the car to somebody else, and it makes it easy to diagnose when there's problems. And it lets, the PPLs are the ones that hide the engine details from us. Hopefully these analogies help. Are there any additional questions before we run on to break? No? Okay, so when we come back, we're going to be covering MCMC diagnostics. So a random walk is great when it works, but there's a lot of ways it can go wrong. Colin showed you some of the good, bad, independent stuff that we just done. We'll show you how to use trace plots and autocorrelation plots and numerical diagnostics to criticize your MCMC run. And then we'll have another break. And then after that, we'll talk about how to do the thing you really wanted to do, which is figure out what the truth of the world is. So after doing all this work, we'll help you get the answers to the research questions that you're asking. So let's take a 5-minute break. Come back by, let's say, 9:55, and then we'll continue on.
We're going to pick back up. So a lot of what I've told you so far have been comforting lies rather than harsh truths. Which, you know, it used to be before 9 a.m. and now it's after 9 a.m. so we're ready now. So the MCMC that we were doing earlier is Metropolis Hastings. It was called one of the most important algorithms of the 20th century by some unknown magazine that we shouldn't really pay attention to, but that's fine. More recently, and the whole reason PyMC3 exists, the whole reason STAN exists is because of advances in this algorithm, advances in MCMC algorithms. And we're now using these gradient-based samplers. And so this is using some information. We put together your probability density function. So you've got your likelihood times your prior. We put that all together, and then we're going to take some sort of gradient of that. Right, so this is just derivatives, and this gives us a lot more information, and we end up being able to make a lot better proposals than we could back when we were using Metropolis Hastings. And so this has led to better scaling out. Metropolis Hastings works in low dimensions, and low dimensions is sort of under 10, I think is what Andrew Gelman often says. So once you're over 10 dimensions, it starts getting a lot harder, and you can either throw your supercomputer at it, or you can use these gradient-based samplers. Just sort of historically, this field has advanced a lot with deep learning because autodiff has become a thing that you can just grab off the shelf. And so PyMC3, for example, came around using the deep learning library that was available at the time, which is Theano. STAN, which has a number of very good developers, is built on top of its own autodiff library. And so autodiff lets you take exact gradients using a program that you wrote. So these gradient-based samplers, I'm not going to get into how they're implemented. I've been, in my own time, I've been working on a series of sort of build your own gradient-based sampler. And so, like, sort of for the rest of the week, I totally encourage you to come chat with me if you're interested in how they're implemented, how to run them. Especially if you're like an astronomer or if you're into like Hamiltonians, you'll see us throwing Hamiltonian Monte Carlo around because we're using this this physical simulation when we're doing this. And so I don't know enough about that, and I'd love to chat more. But I want to show sort of the diagnostics that we worry about when we are using these gradient-based samplers. So the main thing that the gradient-based sampler does that we don't get out of random walk Metropolis Hastings is that it limits the correlation you'll see. And so that small step size versus big step size intuition doesn't really come up in these gradient-based samplers. Gradient-based samplers will flow from one place to another, and it's wonderful, and it's really pretty, and it's fast, and it uses a lot of computing power. So let's see what sorts of let's see some of the ways things can go wrong. Let's compare them to what goes wrong and what goes right when we're using these gradient-based samplers, and sort of build more intuition for how we're going to read these diagnostics. So we're building a model here, and we've got one random variable, which is just a normal distribution. The mean is 10, the standard deviation is 1. And we're going to use that as use that mu as part of the mean for another random variable. So the other random variable will be centered at mu plus 20, and it's also going to have standard deviation 1. So we sort of expect these two distributions to be sort of spread apart by a distance of 20. They both have standard deviation 1. And we expect y maybe to have a little more uncertainty than mu, because y has all the uncertainty that it has plus the uncertainty from mu. Great, and so we can actually just generate this using SciPy.stats. ArviZ, since it's so flexible to allow use with a bunch of probabilistic programming libraries, you can actually just read in Numpy arrays, so you can just make independent samples and then use ArviZ with that. And so let's go look at what happens if we run this with a very bad initialization. So we've got our own hand-rolled Metropolis Hastings sampler somewhere in the background. We're going to start it with a very bad initialization. The one that I showed you earlier, we initialized at 0 all the time, and I used distributions where that wouldn't hurt us. Now we're going to start up at positive 60 and negative 50, which is very far away from the true means of these distributions, of our mu and of our y. And let's see what that ends up looking like. So here's a trace plot, and this looks weirder than any trace plot I've ever seen in the wild. The blue and the orange line look like they're not even on the same plot, but that they are on the same plot. And they're just sort of wavy, they're out there, they're not really doing anything. If we look over on the right-hand side, we might get a clue of what's going on. And can anyone see what's going on with this? So we started a Metropolis Hastings sampler, one at positive 50, or positive 60, one at negative 50. And so what happened to our sampler here?
They both decided to go into the origin.
Yeah. So they're both way outside of the support of these distributions, and they're trying to find where the mean is. And so, but their step size is so small that they can't travel there very quickly. And so we say that these two chains have not mixed yet. So mixing means that they've gotten to the right to where the probability distribution actually lives, and start moving around in there. But right now, all they're doing is moving steadily back towards where the actual probability distribution is. So this is a bad initialization. You'd want to think, if you see something like this, which again, a lot of libraries do their best to automatically figure this out for you. But if you do see something like this, you think, boy, my chains really haven't mixed yet. Those two lines don't look anything the same. We expect them to look exactly the same if we're doing a good job, and they're not even near each other. So what happens if we? So one thing we could do is run the chains longer, right? If they've had the time to come and find each other. Again, we have the asymptotic guarantees. So none of these algorithms are wrong. They're just inefficient. So you can run this for longer, and eventually the mixing would happen. Another thing you could do is try a different initialization strategy. So there's different ways of choosing a starting point, and the starting point that we purposely chose to be bad turned out to be bad. And so maybe we could purposely choose one to be good instead. That's always a great piece of advice. You can also use more chains. One thing you do see in the wild fairly often is if you run this on 4 chains, you'll see one chain that just is off doing its own thing, and that was just a bad inference run. And so the more chains you have, sort of the more you can spot potential problems that you might have seen. Cool. So let's initialize these better. So now we're starting mu at 8 and 13 instead of positive and negative 50. And let's go back and look at this again. And so it was a better initialization point, and you can see this warm-up period where they're moving towards the correct means in the first 25 steps. These first 25 steps we'll call a tuning or a warm-up period. Most probabilistic programming libraries will automatically throw these out for you. I know I was speaking with someone earlier and showing how you can ask the library not to throw those steps out if you really want to look at what happened in your tuning steps. But now the chains look a little similar. That orange one looks funny. It never really gets below 10. The blue one, it's sort of hidden behind orange, but it never really gets above 10.5. And so we might want to zoom in here. Right, so we look askance at these first 25 samples that we got. And so when we're looking at our diagnostics, one thing we might do is zoom in on everything except those first 25. And so what happens when we do that? So we can do that using this fun slice function. This has bitten me before when writing general purpose Python code that slices are built in. It's maybe my favorite built-in though. It's when you do the colon when you're slicing a list or something. You can also do that with just slice. Actually, someone here is from New Zealand too. I visited recently, and every coffee shop has slices, and we just don't have these in America, but they're delicious. And if you go to New Zealand, have some slices. If you're using Python, also use slices. So this is going to draw from 30. So this is equivalent to 30 colon, right? So it'll grab from 30 to anywhere. So none is sort of when you do a colon and just tell it to go all the way to the end. That's what none will do. And so if we cut off those first 30 samples, here's what we see. And we did our fun exercise. So what might be wrong here? We're doing metropolis sampling, and this is what our chain looks like now. Big. So yeah, our step size is probably too big here. So what can we do? So we can tune the sampler. If we spot here that like, hey, it just looks like our step size is too big, but we still only want to take 200 samples, we can go and adjust that. Or you can take a lot more samples, right? We can always sort of lean on these asymptotic guarantees and say that, if I have unlimited time, you often see, especially in older papers that are using Metropolis Hastings, or papers where they can't use gradient-based samplers, there are millions or billions of samples taken, and they just take every like 1/1,000,000th or something. And it's sort of impressive the use of computing power that you see in some of these. So we're going to try that. We're not going to take millions, but we're going to take thousands. And I'm not going to run these live. So this is taking 2,000 samples, or 20,000 samples rather, and it takes some amount of time. This looks a lot better. So now we actually see sort of a normal looking distribution. The trace over here, I'm not seeing any obvious problems. and we're feeling better about what our trace plot looks like. So does that makes sense? So instead of adjusting the step size, I just did the easy thing and sent my computer to do more work. So that's always an option. Here's another one, going back to our very first example where we initialized them very poorly at positive and negative 50. We're just going to do tons of samples again. So this time we'll do 40,000 samples. We again convert our plot to X-array. And then we're going to look at the trace plot again. And here we're going to just discard the first 5,000 samples. So we're going to assume, hey, maybe in 5,000 samples we got to the right spot, and then we'll start sampling properly. And we look at this, it looks like we did a fine job. So this trace plot, you look at it and you say, hey, maybe this is okay. Maybe we can go on to more diagnostics and figure out if we really trust these samples. Again, probabilistic programming libraries do their best to not make you worry about this. I think it's important that you know the work that's being done for you, but you don't necessarily need to know the strategies that are being taken to have this be done. Though again, I'd love to talk about it later in the week. But so here's doing that exact same model in PyMC3. If you just set the step size equal to Metropolis and plug it in here, it'll go and do all of your sampling, and it will automatically throw out all of the tuning steps. And so this will just do a fine job. It'll pick the step size that'll be perfect. It'll pick the initialization points to be reasonable ones, and then you should get good samples just out of the box using these built-in samplers. Stan won't even let you use Metropolis Hastings because they're so bought into gradient-based samplers, which is not a terrible idea. We make it hard to use Metropolis Hastings if you want to. Yeah.
Could you give some insight into like how many draws will we have? Is it always iterative? Like it seems like every chain has the same number of total draws.
Mm-hmm.
I don't see, like in this case, 12,000 being represented in this like sample.
Yeah, so the question is if we have any intuition as to how many draws to use and where this 12,000 came from. This was actually an internal API discussion for PyMC3 for a while. It turns out you have two chains, 5,000 samples each, and 1,000 tuning samples each. So if you do 5,000 times 2 plus 1,000 times 2, that's where the 12,000 comes from. So it's doing 12,000 draws on 2 different cores. And we talked about which number to report, whether 2 progress bars or something, and decided this was the easiest way because people just care about when it'll be done. In terms of doing your own work and choosing how many chains versus how many draws, that's still considered sort of art. More chains will let you explore the space more, but if you have a finite computing time, if you're doing more chains, you'd expect them to be shorter draws. And so the shorter draws have less chance to mix. And so we saw this mixing problem here. Longer chains will mix better, but maybe they'll miss, if you have like a multimodal distribution, they won't explore all of those modes, and you won't be able to explore as many initialization strategies. So there's some balance that you'll have between many chains and many samples. Most examples you'll see in PyMC and Stan use between 4 and 8 chains. There's some really interesting work going on in TensorFlow probability where they're vectorizing your chains. So instead of doing each core, it's just built into the vectorization. And there you can do thousands of chains all at once. And I just don't know how to reason about that. So that's something that people are still thinking about. Cool. Other questions so far about this? We still haven't even seen a gradient-based sampler. I've just been hinting that there's this beautiful thing that we're going to see later. And perfect. So, Richard McElreath has some wonderful lectures online about all of Bayesian statistics, and he has a wonderful blog post on Hamiltonian Monte Carlo, and I encourage you to go read that. It's Better Living Through Physics. David Hasselhoff is involved, and it's just great. But if you just start a PyMC model by default, or start a Stan model by default, it'll choose the samplers for you, and the sampler it'll choose is this gradient-based sampler. It's called a no U-turn sampler. It's based on this Hamiltonian Monte Carlo. And so you can see this auto-assigning no U-turn sampler. Then it goes and initializes. This is the tuning step, and this is where it's choosing all your parameters for you. And then it'll go and run the chains. By default, it doesn't run as many chains as Metropolis Hastings. That's because it's more computationally expensive, but you're getting much better samples while you're running. And so it's okay that you're doing fewer samples when you're using these gradient-based methods because you're getting better samples. And Ravin's going to talk about sort of how I'm measuring better. It's going to be something called effective sample size. So again, we can convert this into netCDF and we can do a plot trace. And this is far fewer samples, but we already get a very good estimate of our theta, of our distribution. And so this is sort of a fast way of doing it, right? The 6,000 samples took under a second, and it's wonderful. And this is what you'll get by default. And so you should hope for gradient-based samplers if you can. If you have any discrete parameters in your system, you're going to have trouble with gradient-based samplers, and there are some other methods that you might want to think about in that case. Mostly getting rid of the discrete variables. There are tons of diagnostics that you'll need. We're not going to cover all of these today. We're going to cover a couple of these today. But these are, ArviZ will automatically collect these in sample stats, and it'll collect similar ones between Stan and PyMC and other libraries if they're available. So Pyro is getting more into HMC, and TensorFlow Probability is getting more into HMC. And so we'll collect a lot of this information. And then ArviZ can implement plots and diagnostics based on having this information. We'll just throw an exception if whatever PPL you use doesn't provide us all of this. And so sort of happy to talk about some of these later and how to read some of these, but just know that the biggest memory usage ArviZ is doing when it's turning stuff into a netCDF file is actually in these sample statistics. So it is in enabling you to do diagnostics if you need to. Great. So for the majority of the exercises, we're going to be looking at autocorrelation plots. And so autocorrelation is a problem that we saw going on in the random walk samplers. And I asked you to sort of see it intuitively. And we're going to get a plot that sort of isolates that autocorrelation behavior. So here's a heck of a lot of math. And this is just saying what's the correlation between a variable and the variable lagged 1 step or 2 steps or 3 steps. And we can go and look at that plot. So this is just using np.arange. And so each plot and like 2 before it is very highly correlated. It's just 2 less than it. And so you see this is what an autocorrelation plot looks like when you have a highly autocorrelated vector that you pass into it. So numpy.arange is just 0 through 500. If we ask it what the autocorrelation looks like, it looks like this. Versus if we do an independent draw of 500 standard normals, this is what the autocorrelation plot looks like. And so there's not much autocorrelation. We hope that independent draws from a normal distribution doesn't have any autocorrelation, and this is what we should think about when we're thinking about what no correlation looks like. Does that make sense? So here's sort of the worst case we could imagine. Here's the best case we could imagine. And so this is building up our intuition for looking at these autocorrelation plots. Questions or comments so far on this? Yeah.
So I assume a partial autocorrelation would drop off pretty quickly with something like this, but that doesn't give us any comfort at all as far as how good our samples are.
Yeah, so the question is a partial autocorrelation would fall off pretty quickly, and then sort of look more like this independent normal. But how much confidence should that give us in our sampler? And that's a really good question. So the first thing you should feel is bad about your sampler, but then you should reflect on what we sort of opened this with is the whole reason we have samples is so that we can compute expectations. And so we're going to be evaluating some sort of loss function with our samples at the end of the day. And it turns out that even if things are correlated, you can often compute very good samples with them. You should just be aware that maybe if they're correlated, you should have more samples. So the more correlation you see, the more samples you should think about getting. Ravin's going to talk about some numerical diagnostics that we do, are these like effective sample size, and that corrects the number of samples you have for how much autocorrelation there is and gives you some idea of how many like actual samples you got. Does that sort of help? So like I always feel bad, but then I remind myself I shouldn't actually feel bad, but then I still feel a little bit bad if there's correlation.
So correlation should be good, right?
Correlation?
Yeah. You want the correlation, and hence the
So
Is that Markov physics correlation?
yeah. So the question is, isn't correlation good? Like we're doing Markov chain Monte Carlo. Markov chains are by definition correlated, and so don't we want the correlation? Yeah. So the Markov chains will introduce this correlation. In a perfect world, we would love to be producing independent, identically distributed samples.
That's the normal Monte Carlo, right?
Yes, and if
I'm missing, I'm just lost here.
Yeah. So in a normal Monte Carlo, which is just running simulations, you might generate independent samples, and that would be great. And so we're pointing out here that when you're doing Markov chain Monte Carlo, you will introduce some correlation just by definition. You're using information about the previous step to generate the next step, and that's what correlation is aiming to measure. That's true, but if you're if you want to calculate your sample, your sample variance of an estimator, that's going to be smaller if you have higher correlation. And so if we really want to lower the variance of our estimator, we want to have as little correlation as possible. So in that goal, we want less correlation. But you're right that this is why we're looking at this, is because we will get correlation from the Markov chain. Yeah.
You get to the result with less samples.
Yeah.
Because they're broken.
Yeah.
I mean, I thought that's what it is.
Let's talk more about that. But yeah, you're making very good points, but I think somewhat nuanced points. Great. So let's go over to the exercises. So these are going to be practicing doing these visual diagnostics. So again, this is notebook 3.2. You can open this up. We've got a bunch of netcdf files already checked in for you, and so you can read these off the disk. Practice making autocorrelation diagrams. There's just a bunch of different good or bad initializations for you to give a try. And if you finish early, try out trace plots, try out other plots. Plot posterior is a nice one, and check them out and sort of work together and get some visualizations going. Cool, and I'll set a timer up here, and then we'll Raveen will set a timer up here, and we'll come circulate for a few minutes.
So I encourage you to work with your partner, be social. Some of this is talking through the plots, not just creating plots. So one thing I'd like to explain real quick. What we're doing here is you're just loading the inference run that we've already done previously. So instead of you guys having to run your own MCMC chains and wait 20 minutes for them all to converge, we've done it prior to this lecture. We've saved them on disk as netcdf files. And this one step will take that file from disk and it'll load it into your computer's memory. So then you can start running, you can start doing criticism on it. All right, so who's got an autocorrelation plot they want to throw up there? So we'll make this one interactive. If you have an autocorrelation plot, throw it in the Slack and we'll talk about what it looks like. And then so someone want to take a screenshot and feel brave enough to throw their plot into the Slack channel? In any one of them. Let's do the first one. And while you're doing that, I'll pull up the answers. So we can make this more than me just talking up here. Let me shut down a bunch of my kernels before this thing complains at me. Close. Cool. So we got one from Morgan and Michael. It's fantastic. So to motivate this again, we want to do Bayesian science. It's really hard to do analytically. I mean, the Bayes theorem came somewhere in the 1700s. Bayes came up with it, and it sort of just sat around for a while because it was really hard to do. And in the last 20 years, we've got all these fancy computers and algorithms that help us. MCMC being the one Colin talked about. And when it works, it's great. But we always want to double check whether our MCMC algorithm works or not. So we'll sort of play the game Colin talked about or did a couple minutes ago or an hour ago. Do you guys think this is a good autocorrelation plot or bad? Who wants to vote good? This is great. We're really confident in our results. I've got the parameters of the world. Who thinks bad? Yes. So this is a scary thing to see. This is probably the worst one I've ever seen. I generated it on purpose, but it is a really bad one. What this plot is telling us is that the chain is very correlated with each other, and we're not really getting independent samples from our distribution. What that means in practice is that based off this inference run, the values we get might not describe the posterior distribution well. In a sense, we're not confident about what our answer is. And as we progress through, well, we'll do one of the checks. We can go back to our notebook here and sort of correlate. So to maybe make this explicitly clear, I ran the MCMC runs in this notebook over here, or sort of simulated them. And what I did was I saved the results so you guys could load them in. So if you want to regenerate these MCMC runs, you can. But I figure, my computer already did the work. I'm going to take the did the notebook clear? Oh, that's not a good thing. So I can take the MCMC runs I have here and then bring them into this notebook. So I'm loading in the one where we had a better initialization. So when our MCMC runs are dependent on where we start. If I start a random walk to Austin in Los Angeles, it'll take me a lot longer to get here than if I started a random walk over in Houston. Houston's much closer to Austin where we want to get than Los Angeles. If we start with a better MCMC, better initialization closer to where our end result would be, we see that we kind of get to our true value much more quickly, and now we have a relatively less correlated run. Now the challenge is I cheated here. You don't actually know what the true value is in practice. I knew where it was because I generated the data, but in reality you wouldn't be able to say I want to get to this location. I'm going to start closer to the location because if you knew the location there wouldn't be any point to doing any of this tutorial or any of the other two Bayesian tutorials in general. If we run the third exercise where we run a really long chain, we sort of drop off a little bit quickly as well. The autocorrelation is less. Now, we're only plotting the first 100 samples here, but you have to remember the autocorrelation plot is using values all the way from the end of the chain that's not being plotted here. And what we're seeing here is that the end of the chain is not really correlated with the beginning of the chain, which is what happens when you run a really, really long MCMC run. Sort of the same idea here. We're still in Metropolis Hastings. This version is not from the janky one that I coded up for the tutorial, but it's actually the one from PyMC3. So it's got more bells and whistles in it. It drops off a little bit quicker, but we still have some autocorrelation at the beginning. The best version is the Hamilton Monte Carlo. So this is the state-of-the-art algorithm. It's the Ferrari of MCMC algorithms right now. And we have very little autocorrelation, and we sort of stay at the beginning. And if we go back to the beginning, and look at how we generated this, we really didn't have to do much work. We really didn't have to do much work for this to go well. We just plug in our priors and our model, and we just run it, and we get good results. This is when people write probabilistic programming languages to you in Stan and PyMC3, we're hoping we get you to this. We want you to just be able to write a model, and then when you look at the autocorrelation plots or the trace plots, things just look fantastic. We don't want you to have to worry too much about the MCMC details. So any questions on autocorrelation? Does people feel confident they could spot a good autocorrelation diagram from a bad autocorrelation diagram? What's a yes? Anyone not feel confident? Okay. The idea here again being you're gonna come across papers, you're gonna come across research. It would help if you can just load the data set real quick and just double check that everything just looks good. Because if you end up writing a definitive research paper on these, I would be very suspect of the results. I would not want this cancer treatment for whoever wrote this paper.
Are there any ArviZ functions that just do all of them, like make one big plot of all the things together?
We do not have one of all the plot things. The reason being is there's a lot of plots. We're covering 3 or 4 in this tutorial. ArviZ has somewhere now, I think around 18 or 19, somewhere in the low 20s, high 10s, low 20s of plots you can use. There's a lot of different ways to look at your data to isolate different portions of your MCMC run.
But I think if you have high autocorrelation like that, it doesn't mean your results are bad. It just means it takes longer to get them, and you just thin it. You just run it for a lot longer and thin it. It's not like it's you're saying you'd be scared of a treatment that had that kind of correlation. It's just more inefficient. It's not incorrect.
it suggests that your posterior run could be biased in a particular way. So yes, you're right. It is not definitive. This is the hard part. It's not definitive that your run is terrible and you have to throw it away, but it would suggest that things could be wrong. And that's the challenge with Bayesian science, is you don't actually know the truth. You're trying to get estimates of the truth. If you knew the truth and you knew how far off you would be, life would be easy.
But that's the problem with MCMC sampling. You never can show that you've explored the space. You could always be stuck in some basin, and if you only did 1 billion samples, you would go someplace else.
Yeah, so it's true, and that's why we have ArviZ and the PPLs. We have all these plots and diagnostics, so you can be much more certain that you have you're in the right space and things are correct. That's an active area of research, and there's a lot of tooling built around. So for the question of ArviZ plots, there's a lot of ArviZ plots, and all these plots are meant to either probably a lot of these plots are meant to help you understand whether you've gotten to either hopefully close to the ground truth or not. It is a problem of statistics in general, not just Bayesian statistics, of figuring out whether you got to ground truth. So even with frequentious methods or neural nets or random forest, right? You can overfit a random forest and things look great, and then you run a diagnostic like a cross-validation or a holdout set, and you realize your samples are terrible. So the whole field of statistics is built around making estimates of your truth and then being sure that your estimates are good estimates and not crappy estimates. If we knew ground truth, all of us would be out of a job. We wouldn't need SciPy at all. That'd be great. We know the physics and the reality and the click-through rate of everything. No more A/B tests. Life would be fantastic. So the downside of these plots is they're very subjective. You have to create the plots and look at a lot of them before you get a good estimate of what's going on. So what we're going to talk about next is numerical diagnostics. So what happened to hard numbers, right? The next problem is one statistician could say an autocorrelation plot looks fine, my results are good, and the next statistician could say my autocorrelation plot, the same autocorrelation plot looks terrible, how could you publish a paper? Visual diagnostics always have that level of subjectivity to them. So to aid with the visuals, Gelman and a lot of his features, Aki and other researchers, all of whom I'm not mentioning here, have come up with numerical diagnostics. So we have two numerical diagnostics here, R hat and effective sample size, and they're basically answering two questions. R hat is saying, did the chains mix well? And effective sample size is saying, did we get enough samples? I want to warn that this is, again, an area of active research. The paper that was published for this was published 2 months ago, sometime in late March. So people are still actively working on making sure to answer your question that, are we getting good MCMC results or not? So R hat, we're going to say R hat. There's another scary math formula. But what this is doing is it's saying, if we run multiple chains, have they mixed well? So the first question somebody had is, why do we run multiple chains? The reason we run multiple chains is if we run 2 chains, one starting in one place and another starting in another place, and we converge to the same spot, we're probably in the right place. So Colin traveled from Boston, I traveled from Los Angeles. The fact that Colin and I both got to Austin means this is probably the right conference we should be at. If I ended up at another conference and Colin was not there, I'd be like, oh, maybe I'm in the wrong place. But we have 2 independent people that happen to be in the same location, so sweet, I'm good. That helps with the trace plots because you can see mixing, but you definitely need it for R hat. And what R hat does is it takes 2 chains, it measures the variance of those 2 chains, and if the variance matches the variance from all the samples combined, you probably have a good plot. If you have one chain that has one variance, another chain that has another variance, and then you combine them and you end up with a third variance number, and you take the quotient of those, you end up with a number that's far from 1. So Gelman has, in his book, Bayesian Data Analysis, he goes into really good examples for these. We'll omit them for the sake of brevity. What you want is an R hat close to 1. And R hat far from 1 means that the variances from the chains are not close. The next one is effective sample size. So there's another problem with Bayesian data, or at least MCMC, is did I get a lot of quote-unquote effective samples? So we could run really short chains of 10, MCMC chains of 10, and then we wouldn't have to worry about computational complexity. It'd be easy, right? You take 10 samples and you're done. The issue being, are those 10 samples really representative of the posterior distribution? Now you could run like what I did before. You could run chains that are like 50,000 long, and then you sit around and wait for 10 days, and you stay in your PhD program for 20 years while you're waiting for your algorithm to converge. And you don't want that either. For me, my boss would yell at me because I can't sit around saying my algorithms are converging for weeks. He'd fire me at some point. So what I want to do is I want to check that I'm running the shortest chain possible, but getting a large, quote unquote, large number of effective samples. The math in this is more complex, and I've just shown you the one term. There's a whole derivation here. But essentially what this is doing is it's taking the autocorrelation diagram, and it's using the autocorrelation numbers to calculate the number of effective samples. One thing to note, this sometimes confuses people, is the number of effective samples could be larger than your actual number of samples. This is just a property. With autocorrelation, you can have negative correlation, and it tends to inflate this number. But generally what you're looking for is a number that's sort of close to the number of samples you've taken. So if I tell my sampler, my PyMC sampler to take 10,000 samples, I want to get some number probably in the range of like 5,000 to 10,000. It's again a little. But if I get a number that's in the hundreds, something is way off. So we're going to relive the horror of the really bad chain, and I'll talk through RHAT. So this is the terrible Metropolis Hastings algorithm we ran at the beginning. It looks nothing like the normals that it should be, and you see this horrible trace plot that's not really well mixed. If I calculate my RHAT here, I get an RHAT of 3, which is pretty bad. When I calculate my effective sample size, I have basically 2.3 effective samples. Given that I've taken a couple hundred samples, 2 samples is not very convincing that this is good. So what we have here is the advice we have from the STAN community. We want to run at least 4 chains. That lets us estimate these RHAT and effective sample size really well. We want the RHAT to be less than 1.01. So they set a pretty strict bar, and effective sample size should be around 400 before you consider RHAT to be useful or not. So these are just the general guidelines that the literal experts of this field have posed that you can use. Of course, in your own field, you should use your own judgment. What I would like you folks to do is we have the next round of practice. So I want you to go through here, and I want you to one, get the results of RHAT and effective sample size for the the same plots we ran before, and then I'd like you to discuss with your partner what you're seeing, whether it looks good, whether it looks bad, and why that case might be.
For the example of the bad initial conditions, if the chains were just run out further, would that converge?
Yes. So the good thing is that is your activity. So you have what you're going to do in this is you're going to run the longer. You're going to check the effective sample size in RHAT for the longer, better initialization, the longer chains, and tune Metropolis Hastings and Hamilton Monte Carlo, and see how using how the starting points, how the chain length, and how the algorithm affect your effective sample size in RHAT. And I will give you 10 minutes to try that out. Let me get through this. I promise we have a break coming up right after this, so your attention span only has to last a little bit longer. But let's talk through the numerical diagnostics. So let me pull up my solutions here, so I don't have to pre-compute them. So let's talk through the first one. So the first one is the Metropolis Hastings algorithm. So this is a Gen 1 algorithm that uses no gradient information. So it's a little bit worse. While it's on paper, it's good. In practice, it's slower than the approach we'll see in a little bit. So when I have a bad initialization and I get my RHAT, the first thing we'll notice is my RHAT ends up being somewhere farther than 1. In this case, it's around 3. This is my first indication that the variances between the 2 chains don't really match. So 3 means that the variances between the different chains don't seem like they're the same, which is an indication that the chains have not converged. My next one for effective samples, I've taken 400 draws here. So the way I'm getting this is I'm from my inference data object, I'm taking the number of draws and I'm multiplying it by the number of chains. So I have 2 chains of 200 for 400 draws overall. And it's telling me that my effective samples is 2. So out of doing a lot of work, I really only got around 2 good samples out of it. So overall, this indicates to me this is a pretty failed inference run. If we move to a better initialization, And remember what a better initialization looks like. So let's just quickly flip back to this one. If I move to better initialization, I have, you'll see, some bad period in the front, but then some nice mixing here. So this is the same object right here, data good initialization. So when I go to good initialization here, my arrowhead's better. I have more mixing, and we can verify that with the trace plot. So I encourage you to take the numerical diagnostics and look at the autocorrelation plot and the trace plot and see what they look like. We get more mixing, but we still don't have that good of an effective sample size. Remember that even though the chains seem to be mixing well, they're in between. The step size is too large. So now let's do the next easy thing. Let's just run a really, really long chain. So I went from taking 400 samples to 100 times the amount to 40,000 samples. This helps a lot. My chains mix well, and I end up getting around 2,000 good samples. So this strategy works. Just run your chains for longer. But if you actually run the notebooks, to do this simple run takes around 30 seconds on this laptop. So if you run this on a larger scale problem, it could take literally days to converge, which is not what you want to be doing. So hooray, we got to the place we wanted to get to for the most part. The bad part is we wasted a lot of time getting there, which is not fun. So now we'll jump from my hand-coded Metropolis Hastings to a slightly better version in PyMC3. So again, I would say refer back to this notebook and look at how we generated this plot. So this particular one, the tuned Metropolis Hastings, came from right here. And in this case, I've just started using my PPL. So I've started using PyMC3 and then using its version of Metropolis Hastings, which has a little bit more niceties. I get much better convergence, and I get around 1,000 effective samples for 10,000. So what is happening here is I'm getting around 10% of my steps are actually turning out to be like quote unquote effective or good independent draws. Still not great. We get convergence, but we still take a while. So the last one is Hamilton Monte Carlo. So this again is the gradient-based approach. It's the sort of the go-to good algorithm these days. This is the no U-turn sample is a version of Hamilton Monte Carlo. And here we get a great R hat, and with only 2,000 draws, we end up with more than half of our samples being effective. So I can take 30 seconds, 40 seconds to get 40,000 samples to finally get convergence, or by using Hamilton Monte Carlo, I can take 2,000 samples, take less than a second, and then get my answer. And so the whole point of this is using these two diagnostics to see how short of a chain, how can I verify that my MCMC run end up getting good mixing and an effective number of samples so I can be confident in my posterior. Questions?
Yeah, I'm just still trying to intuitively understand autocorrelation. So if the algorithm we're using in search to space is finding uncorrelated samples that are uncorrelated in time, does that mean that it's found a flat place in space?
So the question was, how does autocorrelation relate to an MCMC run? The intuition I have here is that if we for the purpose of the example, we'll pretend like we have a peak with a regular normal distribution. So I'll assume my truth looks like this. Keep in mind that in reality, the truth could look like this, and it can be squiggly. But we'll assume the best case, which is a nice single peak. What will happen with MCMC is that if you start far off in the tails, the first part of your algorithm will just be trying to get to where sort of the bulk of the posterior distribution is, where the majority of it is. Once we end up sort of near the peak, now we're just sort of randomly walking around the top. So think about it like hiking a mountain, for example. When you start at the bottom, your steps are pretty correlated. You're usually going hopefully straight up to the top. And now imagine somebody blindfolded you, and the only way you can do this is take a random step. And if the random step happens to be in the upward direction, then you think you did pretty good. Sometimes you'll step down by accident, but generally you want to make it to the top. And then once you're at the top, you'll just sort of circle around the top. That's where your samples start becoming uncorrelated, and you're really exploring where the posterior is. But when you're way off in the planes, you're taking a lot of steps sort of in the same direction, and those are not very good samples because they're not estimating your posterior distribution well. The visualization that probably does its best is when Colin was showing the bimodal one. You can see the steps there. When the trace plot was in a certain area, it was really filling out one side of that distribution, and then once it jumped over, it was filling out another side of the distribution. But if it's always just searching, it's not really filling out a distribution, it's just putting a bunch of samples sort of in a line. Does that help with the intuition?
Yeah.
Great question. Yes?
So for effective sample size, are we trying to target like a proportion, or is this vary case by case on like what is a good proportion overall?
I would say, and this, I'm much more from an applied side, so I'll let Colin take a stab from the theoretical side as well. I usually hope that I reach an effective sample size that are about half as many is what I need. But I would say I'm used to running fairly shallow models, and I constrain my space really tightly. Some of our other colleagues run very complex models, and they're much more stringent. So, do you want to take a stab?
I think that's good.
Okay. I guess I summarized it well. You definitely want to, I mean, if it's very low, like less than 20 or 10%, you're probably very suspicious. But this is why we have multiple diagnostics. It's not one diagnostic just won't give you all the answers. You have to run multiple. The same idea, I'll keep going back to like traditional machine learning because people have that as well. There's numerous types of diagnostics for linear regressions, like mean absolute percent error or RMSE or things like that, because you can use these in conjunction to figure out whether your fit was good or not. Each one of them will give you different pieces of information. Any other questions? Okay, let's take a little bit longer break, like a 7-minute break, and then we'll be in our final section, which is probably the fun part, actually figuring out what all these algorithms do for us and telling us about the world. All right, so shoot for about maybe 12. Sorry, 12 past 11. I'll say it that way. All right, so let's get started in our final stretch here. And so I'm pulling up notebook 4.1. So admittedly, we've taken you on this whole aside. A lot of people come in here, they're like, I want to understand the world, and now we just spent 2 hours talking to you about MCMC and diagnostics, so maybe some of you feel a little cheated. But we're going to come back to the basic question is, how do we make estimates of the world? And so my background is in mechanical engineering, so I like a lot of car analogies. But the way I like kind of partition these things out is your prior is like where you're starting. You're naive and you don't know much about the world, but you want to get to where the truth is. So you jump in. Data is your fuel. So as you pick up more data points, that helps you get closer and closer to the truth. That's how you sort of make your way. And MCMC is one of the engines that helps you get to the truth. So if you've been through Alan's tutorial, he did grid search. Grid search is like the hand crank approach. You're really going for it and exploring all parts of the distribution, and then you've got actually many different inference algorithm types. There's more than we've covered here. There's quadratic approximation, there's variational inference, there's another one called approximate Bayesian computing. They're all engines in your car that help you get to a particular place. The engine we're covering the most is MCMC, Markov Chain Monte Carlo, and we've given you the diagnostic tools to see whether your engine did a good job or not. What we're going to come back to now is, now that you're at the final spot, what can you say about the world? Now that we've done our inference run and run our MCMC algorithm, how much more ground truth do we know about the world? So we're going to show you how to use 2 other types of plots in ArviZ, posterior plots and force plots, to not diagnose the model, but to understand the posterior distribution of your model. So somebody had asked about simulating data. In the first part of the lecture, this is what we're going to do in the instructor portion. I'm going to simulate data. So I have these true parameters of the world. I have an intercept of alpha at 2, and I have a slope of 2. In the real world, you would not know what these are, but for the purpose of the tutorial, I set them, and we're going to pretend like we forgot what they were. What I'm going to do, though, is I'm going to add a little bit of noise. So, the real world is messy. You never get perfect readings on anything. And then I'm going to create a linear regression. And what you end up with is a plot you've probably seen 1,000 times. It's a noisy, linear sort of plot. The trick here, though, is now we want to pull out the parameters of what's going on here. We could do the easy thing. We could use the quadratic approximation, or again, R-squared minimization. And what that would do is that would plot the straight line through here. You would get one straight line through somewhere around the middle, and that's all you would get. That's helpful. But then what it's not characterizing is the noise around the distribution. So maybe this plot could be a little bit noisier. The line would look exactly the same. What Bayesian statistics let us have is it gives us an infinite. The other thing, it gives us an infinite infinite amount of lines, all of which describe the data probably pretty well. And so you get uncertainty to your regression, not just a single quote-unquote answer to what your regression is. So I have my simulated data in X and Y. Here's what the model would look like in math. So if you were going to write this up in a paper, how many priors do I have here? Anyone want to make a guess? 3. I have 3 priors. I'm saying my slope is, I'm starting it with a mean of 0 and a standard deviation of 1. And I'm saying this is what I think my slope is around. I think it's around 0. Just maybe it's an easy thing to pick. I think my intercept is around 0. I think my slope is around 0. And I think my error follows this sort of distribution as well. That's just picks out of hat. There's ways, and picking priors is a whole tutorial in and of itself, but these are relatively what's called uninformed priors. I'm not saying my correlation is negative. I'm not saying my correlation is positive. I'm just saying it's probably, I'll just start with 0 and see where we end up going. What I do is I use the magic of the probabilistic programming language to specify my model. So here are my 3 priors for alpha, beta, and epsilon. And I give it a likelihood. In this case, I'm assuming my data is normally distributed. So I'm not using a binomial likelihood here. I'm saying my y is normally distributed. And the mean of my y is somewhere around this linear regression, and it should have some error that's around here. And I'm feeding it some of my observed data that I've seen. So when we run this, we'll get the magic of probabilistic programming and all the MCMC stuff that Colin showed you and some of you probably fell asleep on. It's all happening under the hood. So most of the time it'll be hidden. You don't have to look at it. People like Colin are working on it, and you just happen to get the finished engine. What we want to do, though, is we want to know that now that we've started with naive estimates of our priors, what did we end up getting? And the tool that people usually grab the most is this thing called a posterior plot. And what a posterior plot gives you is the estimates after your MCMC estimates. It'll give you the posterior distribution that you got from the MCMC sampler. So what we end up here with is 3 different plots, each for each one of our variables. And so here with alpha, we see that we think alpha is around 2.1. This is our intercept. And the error could be anywhere from, it's probably somewhere really between 1.6 and 2.6 with a 94%. This is called highest posterior density. You get that right? And so this is the magic of Bayes. We don't just get the point answer. So if you ran the quadratic approximation, you would just get one answer, right? The answer would be somewhere around, probably around 2. You would just get 2 and that's it. You don't know whether it could be 2.1. You don't really know whether it could be 1.8. You don't know what the likelihood of 1.7 being or something like that. What Bayes gives you is it gives you this nice distribution to say, you know what, the middle is around 2. That's where the mean is. But you know, anything between 1.6 and 2.6 could be the answer as well. We get some uncertainty around it. Just like our planet example, when we had 5 observations, it could be anywhere between 10% water, 90% water. But when we get a lot more observations, we're pretty sure it's around 0.4, which is right in the middle. The nice thing is we get that for every single variable. So with our pretty standard regression here.
So the likelihood for the data, did you say it's also normal?
In this particular case, I'm saying the likelihood is also normal.
It shouldn't be flat.
It could be anything. You get the choice to pick your likelihood function. I decided to pick normal, and that's fair. This would be the sort of criticism we'd have back and forth of whether my model is good or not. I think there's the famous aphorism that all models are wrong, some are useful. In this case, this model is useful enough for me to explain Bayes in this tutorial, and that's what I'm going to go with. And in reality, if we were doing real research, then we would have this argument of whether the model is useful or not.
I mean, for the parameter of the fit, alpha, beta, I mean, normal, and that's what they are, and we know that for sure. But the data, normal, is interesting.
So to repeat the question, because I didn't, why did I make these choices of priors and why did I make these choices of likelihood? You actually, in reality, you won't know what the data looks like at all, right? That's the whole point of statistics, again, is making these estimates.
We're talking about linear regression, so we know the slopes and the betas and this. So it's a good choice for normal.
Okay.
And that's fine, but the data itself.
So, this is important. I'm not saying the data is normally distributed. What I'm saying in a linear regression is that any one of these, if I take a slice here, this mean as this slice is normally distributed. So I'm not saying it's normally distributed in this sort of x-axis sense. I'm saying that any point along the line, the data follows the normal distribution. So that's actually, sorry, a subtle shift that to make up there. That's an excellent point. Yes, the data, when you look at it this way, it looks linear. But what I want to characterize is the mean and the standard deviation at any point here. And we'll have a really good example in this. So this one looks pretty standard. I have a good estimate around my beta. So my MCMC algorithm says my beta is somewhere between 1.8 and 2.0 with a 94% highest posterior prediction, and my mean is probably around 1.9. And I have some characterization of the noise as well. So I've sort of understood the parameters of my model more. I start at 2, and for every step I take in the x-axis, I gain 2 for linear regression. With ArviZ, sometimes you don't care about the noise parameter. We just want to focus in on one particular variable. So you can pass in var names equals beta, and I just get my beta distribution. So forest plots are another way of looking at the data. Forest plots are great because they sort of collapse it all into one shot. So if you take your posterior distribution and you sort of just smash it down, that's essentially what a forest plot gives you. So it makes it easy for me to see that my alpha parameter, my intercept, I'm relatively unsure about, but I'm pretty sure about my beta being somewhere between 1.8 and 2.0. And I can really get a sense of that here because the alpha is pretty widespread from, it's a little hard here, 1.6 to 2.6, but my beta is much smaller in here. Same with my epsilon. As a nice bonus in ArviZ, we also give you ESS and R-hat, so you get a nice one-shot diagnostic. Somebody was asking about getting as much into one plot as possible. Forest plot is definitely one of those plots in ArviZ where you kind of get all of it in one. So it's pretty handy to just show this plot. And we also have a tabular summary as well, if you don't like plots and you prefer numbers.
So what happens if you know what the errors are on each point? If you have some estimate of the errors on the y-axis for each of the points on the plot?
When you mean arrows, can you specify?
You have,
oh, you know the errors. Okay. So if you know the estimates, you can do one of two things. Instead of setting this as a prior, what you could do is you could go in here and say, I know the standard deviation of my error is 2. And you could say, I'm not going to estimate the error at all. I'm just going to say it's 2, and I'm done. So
what if each measurement is a different error?
That's a good point. So we'll talk about that in a second. So there's PyMC3 and some of the other PPLs have mechanisms of working with that data. So you can do the thing where you say I don't want to estimate error at all. I know it's this much, so I'm going to put it in, and that's it. That's that. If I knew my slope, I could even just throw the slope in here, and I say I know the slope is 3. I'm only going to estimate the intercept. Totally valid. That's the type of model you chose. Or you could go in here and you could pick a different distribution and really set what's called an informative prior and really push your model to go one direction. So the next question people have, which is I'm going to allude to here, is what if you have something that looks like this? This is a heteroscedastic plot, as it's called, and what's happening is the error is increasing over time. In manufacturing, this is actually really common. That's why I have this plot in here. When you set an iPhone processing line, when you first tune your iPhone like screen clamping machine, it's really good. But over time, the machine wears, and then you start reaching errors to your iPhone, and it becomes a little sloppy. Same with your laptop. The first runs are usually good, and then over time, the machinery wears down, and then your error in your Mac machine, like the physical manufacturing of it, grows over time. And so we have something different here, and let's be intuitive about this before we go on. One thing I can see here is, well, I seem pretty certain about where I'm starting from, right? My starting point is within a very small boundary, but as I grow larger and larger, I become more and more uncertain about the slope of my growth. I don't know if my slope goes this way or this way, but I know that I start somewhere around 2. Again, I generated the data here, so my slope is at I might have mixed this up, but my slope and my intercept are at fixed values, and then my noise is increasing over time. So you can see here, my slope and my noise are both multiplied by x, which is why I'm able to generate a plot whose error increases over time. So how do we fit this type of model? Well, I made one subtle change here. In my model, since I can sort of see that my data is distributed this way, I've said that my standard deviation increases as a function of x. So I've changed my specification for my error right here slightly, but I've left the rest of it the same. This is what makes it a heteroscedastic sort of Bayesian model. What happens here, though, is when I get to my posterior plots, you'll notice that now I'm actually pretty certain about my alpha. I'm pretty certain about my intercept, which is the intercept term right here. But I'm way less uncertain about my slope. And it's hard to do on one screen, but if you pull these up with your partner side by side, you'll see that the model is sort of flipped. It's really sure about where we're starting, but it's really unsure where we're going. The other model is pretty sure about where we're going, but more uncertain about where we're starting. And forest plots and posterior plots are what would help you sort of get this sense. So my alpha, I'm pretty sure starts between 1.9 and 2 with a 94% highest posterior density. But with my beta, I'm relatively unsure what the real slope of this line is. And so this is what all the magic of MCMC and Bayesian statistics gets us. It gets us to these plots where we can really get a sense of how confident we are about our parameters. When you run a lot of other algorithms, like let's say like neural nets or the point estimate algorithms, you get an answer like a binary answer, yes or no, and maybe some small handle on error. Bayesian statistics is the type of statistics that really gives you an estimate of your error over all possible parameter values, not just the one that the model happened to give you. All right, so since I'm the more practical guy, I don't have a PhD like Colin, there's ways to use the results, and I've actually used some of these in practice. So if you need to make a yes or no answer, Krishi gives you a framework. It's called region of posterior equivalence. I won't go into it too much, but it helps you make a sort of frequentious type decision of significant or not significant. I want to point out that even in frequentious in statistics, the p-value of 0.05 is a completely subjective decision, and there's a lot of assumptions baked in. The nice thing is it just helps you make the answer, helps you get an answer. There is a framework that has been proposed as well. For me in particular, I'm actually I like Bayesian statistics a lot because you get what's called a loss function. So I can say if we end up getting something in this range, if we end up getting a part with like a 3.0 inch, we'll lose this much money versus this much money. So when Colin had the profit chart earlier, that's actually what I use Bayesian statistics for. I estimate, so I work at a restaurant now. The thing I can do is estimate the amount of people that are going to come into a restaurant to decide how much food should go into that restaurant, for example. So at Sweet Green, we have fresh food. If 10 people come in, we want to have enough food for 10 people. If 20 people come in, we want to have enough food for 20 people. We don't know how many people are going to come in, though, so do I overestimate and all the ingredients go bad, or do I underestimate and people are angry with me? People being angry with me has one cost, and that's the shortage. And us losing food has another cost. That's the wastage cost. I can use these distributions to calculate the optimal inventory to balance the two costs. That's really, really why I like Bayesian statistics and why they've been helpful for me. And then the last thing I want to point out is that bad models and bad inference leads to bad decisions. So I know we spent a lot of time on the middle section of this tutorial. If you have a bad inference run, you can't really trust these plots. So you can try. I actually encourage you to plot some of the inference objects that we created for you earlier and see how different they are, even though you have exactly the same ground truth. With a bad inference run, you can't be really sure you're in the right place. That's why diagnostics are so important. Use the diagnostics to check whether your inference run was good, and once you're pretty certain there, you can then use posterior plots and forest plots to then say this is what the world looks like. So for the last activity, what I would like you to do is I'd like you to estimate the effect of fertilizer on plant growth. So I've simulated some data sets for you here. The motivating example is, your grad student friend also really likes plants because millennials learn to plant these days, so I've heard. And the way that this experiment is run is once the plant reaches 10 inches high, so it's a fairly healthy plant, your friend treats the plant with one of 3 fertilizers. And the fertilizers hopefully help the plant grow. You just want to tell your friend which one helps the plant grow the most. So for the question earlier, we are not estimating the intercept here because in this particular case, once the plant reaches 10 inches, that's when we treat the plant. So I don't need to know the plant is 10 inches. I've measured it with a ruler. What I want to know is that once it's reached 10 inches and I do a treatment, what's the slope of the growth of that plant afterwards? So I'd say get with your partner and try and answer these quote-unquote practical questions about the effectiveness of this fertilizer. A hint here again, the slope is what will tell you the effectiveness. So I'll give you around 20 minutes. We'll make this a little bit longer one. And feel free to bug Colin and I with questions.
Just a quick note, because we had a couple of questions about this. The HPD interval is 94, just to point out that it's not 95 and that it's settable and that it's not a confidence interval. So it's 94 on purpose. It's sort of like the 19-mile-an-hour speed limit on college campuses. It like makes you notice it and think about what you're doing rather than just like defaulting to 95. So that's why there's that 94% HPD.
And show you what this looks like. So the goal here is to figure out how much fertilizer affects our plant growth. And so we have some data, we have some MCMC runs, so I did that portion for you already. And we want to see is which fertilizer seems to do the best. So we have the green power fertilizer, and when I look at my slope, so let me go up here, my slope is over here, beta times x. For this particular fertilizer, it looks like it does a pretty good job, 2.8, and the range is anywhere from 2.6 to 3.0, and it's got some noise. But it looks pretty noisy. There's a lot of, the epsilon is the standard deviation parameter. So while it seems to do around 2.8 units of growth per day, it could be anywhere between some wide range. If I look at my budget fertilizer, who thinks this fertilizer does a good job or not? So this is estimating -1. We're pretty sure this fertilizer kills our plants. Which is the opposite experience we want. But this is the power of Bayesian modeling, is you can sort of make those estimates, and the noise is relatively low as well. And the last one we have is our roots galore fertilizer. It seems like if I look at my 94% highest posterior density, again, this is a totally arbitrary thing, which is why we made it 94. But I'm like 94% sure that this fertilizer is very consistent with 2 units of growth a day, and my nose parameter is very low as well. It's a little hard to squint and see these plots, especially on this screen. So we then have forest plots, which then show this to us. So our green power fertilizer is fairly noisy on the epsilon parameter. But our budget fertilizer has less noise, and our roots galore has almost no noise at all. It's very, very consistent in its growth. When we look at the slope parameter, though, green power is pretty high up there with 3 units mean. Again, it's noisy, so it's not always going to be 3 units of growth a day. Sometimes it'll be a little bit less, sometimes a little bit more. But it looks like, on average, our plants will grow about 3 units a day. Our budget fertilizer definitely seems to kill our plants pretty consistently. And our roots galore is very consistent. So there's almost no error on the slope at all. It's very confident that it's at 2. Here we have the tabular data where you can connect everything up as well. So instead of having to look at plots, you can put this all into one shot. We didn't cover all of these diagnostics here, but you also get some of the effective sample size and all of that. So you have your results with your posterior estimates, some measure of error. It's important to note that the summary makes an assumption that your model is normal. Not all models have normality, so you shouldn't just jump to this and make a conclusion. I would advise that you plot your data with a posterior plot first, see if it indeed is normal, and then if it is, then you can sort of use these values. Giving recommendations to your friend. Green power looks like it's the best. Budget fertilizer is the cheapest, but definitely is like the one that's not useful at all. And so this is the full scope of Bayesian analysis. This particular tutorial goes through the PPLs and how to diagnose MCMC runs. So when you get good MCMC runs, you can then use these uncertainty estimates. One really good question I got was, why would you want any of these uncertainty estimates? So coming from an industrial engineering background as well, there's this classical problem called the news vendor model. And what it's saying is that you can buy a newspaper for 10 cents and you can sell it for 15 cents. How many newspapers do you buy a day? So you don't have any sitting around because they'll go bad, but you don't buy too many and then lose out because nobody bought those particular person's newspapers. And what happens in the lectures is they give you the demand distribution. They say the demand is 20 per day and it has some standard deviation. But I've never worked into a company where somebody just handed me the distribution of what the company looks like. What they hand me is a SQL table with a bunch of orders in it, and they say, go figure it out. That's your job. So what Bayesian statistics helps me do is understand that, in this case, characterize the latent parameter of the world, and maybe in this life it'd be how many newspaper a day are people going to buy so my company can stay in business and I can keep my health insurance. What I want to
Which parameter is that?
yeah, I know, that's the Bernoulli one. We didn't cover it in this tutorial because we had a lot of content. A question that came up a lot is, how do I choose priors and how do I choose likelihoods? I know you had asked about how do I pick a likelihood, and other people had asked, how do you choose a prior? While we covered MCMC diagnostics, whether an inference run went well or not, there are also model diagnostics. So is your model a good fit for the data? These are leave one out, and information criteria, which helps you say, is one model better than another model? I'll leave this content here for you guys to go in your own time, but we could reparameterize some of the models we had in the past and see whether they were good models or not. In particular, I want to point out that in our estimating plant height model, we can estimate whether our plant height grows linearly. Spoiler alert, plants don't grow linearly. At some point, they top out. We don't have plants that are infinite length long. At some point, they top out. So intuitively, we could say that a logistical a log model fits better than a linear model. And you can go through and see which fit is better and use information criteria to make that judgment with numbers and math and pair that with the subjectivity. With that, I'll leave it open for questions for about maybe 3 or 4 minutes, and then I'll close.
You didn't address how do we get uncertainty into our observations.
So when you mean uncertainty into the observations?
So if you go to your, say you measured, in this case, you measured your plant heights. You measured them throughout the day.
Yes.
There's some variation in the plant heights. How do you code that back in?
So in this particular case, the uncertainty is coded in our error estimate right here.
I get that.
Okay.
But if I have an instrument and I take measurements of that instrument, I know there's uncertainty associated with that instrumentation.
So that's a good point. What you could do is you could split this uncertainty up into multiple errors, things that cause multiple errors. So one is the plant height will grow, the plant itself will grow at an uncertain height, and then the ruler I'm using could also have some uncertainty. You could have 2 uncertainty terms here, and they could be additive, or they could be multiplicative. It's your choice as a Bayesian modeler how you want to combine these sources of uncertainty together or how you want to model them. So I was lazy here, and I grouped all the uncertainty together in one, both plant height uncertainty and ruler uncertainty. But if you want to become more sophisticated, you could have a prior for your ruler uncertainty, and you could have a prior for your plant height, growth height uncertainty as well.
And when you're doing stuff like that, that's also when you should worry about model identifiability, right? If you just split everything up arbitrarily, finely, you can get some weird geometries when you're deciding how to divvy up all the errors. But if you have some way of determining which error came from the ruler uncertainty and which came from the plant growth uncertainty, then you should be fine still. So you do have to think a little bit about the modeling choices too.
That's a really good question. Thank you. Any others? Yes, sir?
Are there any tools in the package to draw from the posteriors and do posterior predictive checks?
Yes, so this is a great segue. So we covered a very small slice of ArviZ's functionality. To repeat the question, is there anything that helps you do posterior predictive sampling? So to illustrate the question, so everyone gets it, I'll go back to my one of my very first slides. So we covered one box out of this whole thing, which is just evaluate and criticize the model, but you still have additional things like here, generating posterior predictives and all of that. ArviZ has a lot of functionality, one of it being plotting the posterior predictive checks. So in PyStan, what you can do is now that you know your slope of your plant growth, you can now estimate what your plant will look like on day 20 and day 30. And you can simulate the future. That's some of the beauty of Bayesian data science. So I can simulate how many people are going to show up to Sweetgreen a day by seeing how many people showed up to Sweetgreen in the last week. ArviZ includes the posterior predictive checks and the plots to help you there. We hope we have a well-featured gallery and documentation where you guys can poke in here and see some of the additional plots that are there and useful for you to use in your Bayesian journey.
We should probably let you go now, but I think Raveen and I are going to be sticking around if you have extra questions. But thank you all so much for coming.
Oh.